We've got session 4 front screen. Is that looking all right?
Yeah, all good.
Perfect. Cheers, mate. Okay, let me crack on. So good afternoon, everyone. Apologies for that stilted start. That's how these things go. Welcome to the afternoon session. I didn't get a chance to look at the names. I don't know how many of us are returning from this morning, how many of us are new to the call, but thank you regardless of whether you've been here all day or you just joined this afternoon, or indeed watching it back later. We're recording these sessions and they'll be available for free, as with anything that we do CPD-wise, to watch back later as well. So yeah, hopefully we've got some folks checking this out in the future. This afternoon, I've got a couple of bits to do. First of all, I'm going to talk about fire risk assessment. Now, I'm talking about fire risk assessment as we know it in the fire sector. So what we do in terms of occupied buildings and how we risk assess those. And in the lunch break, I took the opportunity to drop in a few slides about something we touched on earlier, because I've got the opportunity to speak to so many structural engineers here, which I don't normally have the privilege to do. So I'm going to also talk about fire rating of structure of buildings, because I think it's an important one. This morning, what we've done is kind of high-level overview of our disciplines, what we think people ought to know. This afternoon, it's the same kind of things that we think people should know and things I'd love to tell people about fire. So a bit of a takeaway today from a structural perspective. You'll see when I come on to that. I've kept this slide in though. Sentiment is still there. If you've got any questions about fire engineering, that's what this is about. This again is an open forum, me and Sean having a note sharing session and just getting you guys in as well. So do feel free to ask questions. That's what this is all about. This CPD is totally free. We funded it ourselves through Delta and SPH, and it's just about giving back. So please do use us while we're here if you have questions you'd like to ask. For anyone that wasn't in this morning, I won't do the full intro again because you can catch it on the other video. I'm a fire engineer, so my name is Joe Hart. I hold a number of different roles. Principally, I spend time in both academia and in industry. So I'm the founder and group director of a bunch of Delta businesses, the group director of Delta Innovation Group. So I have my fire engineering team. I'm head of fire engineering, working on fire engineering design. I'm also head of research and development at Delta R&D and chief instructor at Delta Fire Training. So I spend lots of time leading those businesses. We have 2 other businesses in our organisation who do fire risk assessment handily, because I'm about to talk about FRAs, and Delta Fire Protection, who install passive fire protection as well. So across Delta, we do lots of different things in fire. This isn't a sales pitch, so I'm not going to tell you about the businesses. It's just to set up why I'm here talking about it. And I spend a few days a week, a couple of days also lecturing. So I teach fire engineering at the university. I know this morning we had some students on. Good to see you guys. Some familiar slides here, actually, if you've been through the programme. It's some of the stuff we touch on in the degree course. So again, from this morning, I said, of the thousands of slides that I present, this is the one I do most often. So across hundreds of different lectures, I always do this one, and I talk about fire engineering being multidisciplinary, none more so than in this lecture as well. To pick up the point, again, for anyone that wasn't in this morning's session, this is how I see fire engineering. It's a mix of multiple different disciplines. We have to, in making decisions about fire, draw on our knowledge of all of these different areas. We've got chemistry, biology, physics, architecture, maths, risk assessment, structural engineering, all of these things. We don't have to be masters of these, but we do have to know a little bit about them. Again, a bit of the ethos behind what Sean and I are doing at the moment with our CPD calendars and stuff that we're sharing, going to conferences and speaking about things, is to share that knowledge so everybody can gain from it, because I benefit from so many people in these industries who help me become a better fire engineer. I hope we get the chance to do the same with fire engineering, reciprocal a bit this afternoon. So those are the intro slides. We pick up again with law and history of fire regulations. This morning I talked about where our regs have come from, and I need to do another one to get us to fire risk assessments, because I have to kind of frame it in terms of this idea that we develop legislation and standards and the industry develops based on real events and real fires that occur. We spend a lot of time analysing real events. So anybody in fire will be familiar with this case study, I trust. Many of us outside of will be as well. Anyone who isn't, it's a really good one to understand, because it was one of those sea changes. Sean mentioned this morning when we were chatting about Ronan Point, I said it should have had more impact on fire, and I do still believe that, but we look to these big notable case studies and see what impact it had. Saffron Walden, the Rose and Crown Hotel fire, was a huge one for us in fire. So back Boxing Day 1969, there was a really significant fire at a hotel premises called the Rose and Crown. At the time of the fire, there were 33 occupants in the building, 11 of whom, there were 11 fatalities in the fire, so 11 of whom died in the fire. It was a relatively small fire when you consider what caused it. It was the burnout of a television in the hotel lounge, and it spread throughout the hotel and caused the 11 fatalities. There was a huge rescue operation and a huge firefighting operation, and it was sort of unheard of at the time in terms of fire statistics and what was happening, much like the Grenfell, much like Ronan Point and other fires that we investigate. And much like when we have these significant fires, we fast forward 18 months, my 18-month rule I was talking about this morning, and we see what change came about. We see what the impact of that fire was. And for this particular fire, there was a huge shift in fire regulations in history that leads us towards our fire risk assessments we have today. And it was this, the Fire Precautions Act of 1971. So an Act of Parliament was passed to say that we must do more to risk assess, accredit, sign off, design, manage buildings for fire safety. And it was because of the proportionality of the Rose and Crown fire, because it was such a significant incident, more onus was put on fire safety. And one particular element of the Fire Precautions Act, you can study the Fire Precautions Act in a great amount of detail, but one area that was brought in particularly is referenced on screen, the idea of fire certificates. So following 1971, we began to issue fire certificates to buildings. And it was where the local fire authority would go and investigate buildings on their patch and issue a certificate to say, this building complies in terms of means of escape, firefighting, staff training, management of the building. It was centralised to local fire brigades and fire services, and they would go around, they'd carry out these surveys and they'd issue the certificate if they were satisfied that fire safety was being appropriately managed. Now, this was in place from 1971 right the way through to the 2000s, and this was the standard approach. It was a big part of the fire service non-intervention strategy, so not operational firefighting, but in prevention and in protection. And this was in place right the way up until 2005. In actual fact, 2006 is when it was enacted, where we have our current standard for risk assessment of buildings for fire safety. And when I say risk assessment here, there's some bipolarity between what I'm going to talk about and what Sean's going to talk about for structures, because we have fire risk assessments very different to a structural risk assessment. And I sent Sean one of our FRAs last week before we met for breakfast, and he read it on the train up and then very kindly spent breakfast telling me how it's not a risk assessment, and also posted on LinkedIn that it's not a risk assessment very kindly as well. And it's true, it's not a true risk assessment in terms of the probabilistic methods that we use in design. And I want to highlight the difference between a design risk assessment and a fire risk assessment in this talk in the next few slides. So 2005 occurs, the Fire Precautions Act is in, we're issuing fire certificates, we're reviewing buildings, the local fire service are reviewing buildings. And in 2006, from the 1st of April, that onus for fire safety was decentralised. So it was decentralised away from the fire service to the building owners themselves, the people that are in charge, what we call the responsible person. So in every building thereafter, there was a responsible person who had to look after fire safety in their own premises. They decentralised safety. If you go back to the 1970s, the same thing happened with health and safety legislation. So the Health and Safety at Work Act decentralised safety and said everybody has a duty, everyone has a responsibility for their own safety and those around them. And if anybody who employs people or employs subcontractors, or if you work for somebody even, because you have a duty as well, you will have signed a contract, you'll be aware of your duties under the Health and Safety at Work Act. Fast forward to 2005, in fire we get similar, decentralised, everyone's got a responsibility for fire if they are in charge of a building. And the particular duties they have are shown in Articles 8 to 24. It gives different responsibilities in terms of you must train people who have responsibility for fire safety, you must keep records of various things, you must maintain suitable means of escape in the building, you must maintain suitable firefighting conditions, your detection system must be maintained. The example on screen there, Article 21, is specific for training. So when people join your organisation, you have to give them fire safety training, and if risks change, you have to retrain them and make them aware of those risks. And there is one clause in there, one article in the regulatory reform fire safety order that underpins fire risk assessment as we do it currently in industry, and it's Article 9. Now, Article 9 has been updated slightly in 2021 when we've had the Fire Safety England regulations, but at its base, at its heart, since 2005, it has said that the responsible person for a building must make a suitable and sufficient assessment of risks to which relevant persons are exposed. So there now becomes a legal duty for anybody who's got this decentralized responsibility for fire safety to do a constant risk assessment. It's not an annual thing. It's not every year bring in a risk assessor and get the survey done. It is a duty to constantly be assessing fire risk. And there's a number of reasons for that, and I'm going to touch on those throughout the rest of the talk. But the principal one that comes to mind is because fire safety risk changes throughout the building life cycle. In the course of a week, you might have a really busy time in an office on a Monday. No, Mondays are quiet days. Tuesday, really busy. Friday, there's nobody in. You have a change of risk profile throughout daily, weekly, monthly in a building, and changes in risk associated with fire safety as well. So under Article 9, as of 2005, we are constantly risk assessing buildings for fire safety, and it's a legal requirement. Now, what that looks like, and I'm going to present the way that we learn and the way that we teach fire risk assessment for this ongoing management of buildings, is exactly like this. And this is the highest level risk assessment. And then Sean's going to come in and do loads of technical stuff to build on this as well. But this is the simplest form of it that we have. So in doing a risk assessment, we identify the hazards. A hazard's something that has the potential to cause harm, as most of us probably know. And the risk of that hazard is the function of the likelihood of it occurring and the consequence if it does. So if we go out and do a risk assessment of a fire exit and it's locked, let's say it's chained shut with a bike lock or a padlock or something, the consequence of that is very high because that's a means of escape and you can't leave the building. And the likelihood of that causing an incident can go one of two ways. You could say it's very high, it's very likely, because if somebody goes to that, they're not going to break through the lock. But then you could also look at it and say, well, how important is that means of escape? What's the likelihood of a fire occurring in the first place and it needing to be used? So there is ambiguity in the risk assessment process, but broadly, we seek to identify a hazard, consider the likelihood of it occurring, and consider the consequence if it does. And that's plotted on a matrix, something similar to this. Probably familiar to us as designers, this sort of matrix. Let's say we've got something that's very likely to occur and severe, like that chained up fire exit. What we seek to do is reduce the impact of it, reduce the consequence or the likelihood, and bring it down to alarm, possibly, bring it down to an area where we're comfortable, certainly reduce any high or medium high hazards. So the simplest form of fire risk assessment under Article 9 would look something like this. Some principles we adopt in fire more broadly, not just in this risk assessment, but also in fire engineering, is it's not possible to remove fire safety risk. Fires happen in all buildings. Throughout the life cycle of the building, it's likely there will be a fire at some stage. Throughout all the history of the built environment, there have been significant fires and minor fires. We talked this morning, and I'm going to try not to hark back to this morning too much for anyone who wasn't in, but we talked about this idea of survivorship bias. And fire data we have is inherently skewed because we don't know how many fires there are, because we only log it per building, of course, or we log fire service attendance rates. So we don't necessarily know how many buildings there are. There is no duty to report a fire if it's small and we put the fire out ourselves and nobody's injured. So we accept that fires will occur in buildings. We always design buildings on the basis that there is a fire in there. And we were considering, or we were talking earlier and saying, we consider the worst case, but we can't always define what the worst case is. So there are usually multiple. So in doing the risk assessment process, we consider what if there is a fire in the stair, really high consequence, relatively low likelihood, possibly because the stairs are usually sterile. But if it does occur, it's got a huge impact on our building. That might be case scenario number one. Scenario number two might be a fire in a flat, which is going to be far more significant. But if the building is installed, if everything's installed correctly, the building's designed correctly, it should be isolated to that compartment. And we design other things into the building to protect that. So lower likelihood that it's going to impact somewhere outside the compartment of fire origin. So the main principle we have is that fires will always occur. We can seek to reduce the severity of them by breaking buildings up with compartmentation, putting sprinklers in, things like that. And we can seek to reduce the likelihood by making sure things are tested, maintained. We isolate fire risk, but we're not designing for a zero case. We accept there's going to be fires in there. Even the best designed building, as it says at the bottom, will at some point have a fire. And as a designer or a risk assessor, we have to consider that. Now, in doing the risk assessment, and this is the constant process of risk assessing buildings, as well as documenting that perhaps annually or every couple of years, this is just what all buildings have to do under Article 9. We consider different types of risks that might occur. And we break these down really broadly. And again, this is really high level kind of content at this stage, into what we call active and latent risks, or active and latent hazards. So an active risk would be something like the wedged open fire door. And I've never done a fire risk assessment where there wasn't a wedged open fire door. It's held open with a wedge like that, or it's tied up with a shoelace, or there's a fire extinguisher holding it open, which is always the ironic one, or it just doesn't fit flush in the frame. It's an active risk that we can go in, kick the wedge out and fix it there and then. These are things that the day that you install a building, the day you open, on day 2, it's likely that's going to happen. These risks are just come about in the opening of buildings, the operation of buildings, sorry. And then if we're thinking more about existing buildings, we also have latent risks or latent hazards, things that are just there all the time. So a single stair condition, an unsprinkled building, an existing building with defects in it, cables that have been knocked through a hole, through a wall and not been fire stopped appropriately. We have those inherent in the building, as well as active risks that we go in to identify. And in our fire risk assessment, this is the constant process, or that annual review, or the frequency of the review is to be determined by the responsible person. It's to highlight and rectify active risks. So we write in the report, it's a high risk that you've wedged that door open because it opens into a stair. It should be fixed immediately. Nice, easy solution though. Remove the wedge, put a sign on the door saying do not block, do not wedge open, whilst also providing mitigation for latent risks. So if we've got an existing building with a single stair and it's above a certain threshold height, the action isn't necessarily fit a second stair, or the building's unsprinkled, so fit sprinklers. This is where we apply some risk assessment methodology and design work, and we say, what's the risk that we've got there and how do we mitigate it? So if it's a single stair, for example, the risk is, well, we've only got one means of escape, so we need to protect that stair. So we can put additional measures in, like a ventilation system, some pressurization, ensure that that stair is robust, limit travel distance to the stair. This is the essence of fire strategy guidance. We seek to mitigate latent risks and active risks as part of this FRA process. We try to rectify insofar as we can. So a couple of slides I'm going to blitz through really quick. When we're doing this risk assessment methodology, we identify the severity or the consequence of the hazard that we've identified. This could be quantitative. We could say it's a financial loss, it's a delay period. We could seek to quantify it ourselves on a matrix basis. We could say that it's more severe than another consequence. Or it can be qualitative. It can be reputational damage, resource impact, injury or fatality, business continuity, operational continuity. We can seek to demonstrate what this severity is ourselves, or we can use a basis whereby we compare them. So it is more severe. Scenario A is more severe than scenario B. That's something that we might do. So in quantifying the severity, we have a number of methods available to us. And the likelihood we touched on this morning, again, for those that weren't here, apologies, but we were looking at some graphs and thinking about how likely it is that fires occur. We can look at quantitative data. So we can say it's likely we would have a fire in this environment because of the inherent risks we've got, because of the processes that are happening. I did a fire risk assessment for a recycling centre not very long ago. And I said, one of the questions on the risk assessment form is how many fires have you had, or what's your history of fires? And they showed me their last 4 fires on CCTV, and they were in the last month or so. They have one a week, and it's batteries that are being disposed of incorrectly, and they go up, and they're really, really likely that they have fires in that space. So what we had to do was we didn't have the opportunity to reduce that likelihood. It was an inherent risk in their building, in the operation of their building. So consequentially, we thought, well, let's reduce the severity of that fire. No combustible materials can be stored in and around the compactor that you've got. We put a sprinkler system in, so you reduce the severity of the fire. We didn't do anything to reduce the likelihood. And in fire risk assessment and in fire strategy design, this is a really common approach that we take. So we seek to reduce one or the other. We can't always have, we can't always reduce to 0, and we can't always impact both. And actually, I think this is probably the best way of describing it here, because this is quite a common one we have in fire strategy design. If we have a fire escape route that goes over a roof, a flat roof, that's quite commonplace that we would do that. And there's a particular building I have in mind as I'm saying this. I won't say what building it is, but it's a building where they had a really high population density that went out onto a flat roof and continued into another stair. 5,000 people, it was an event space type thing. And we had to do a risk assessment as part of our design to say, well, how do we mitigate that risk? And this isn't a photograph of it. I've plucked it from Google, but it didn't have any of these barriers up. And when we're doing our risk-based design, we were saying, okay, well, there is a really high likelihood that if people are escaping across that space, somebody will go over the edge of that roof, because there was no edge protection, no barrier protection, no lighting. It was just a flat roof on top of the auditorium. And the severity of that was really significant because it was a 10 meter, perhaps slightly less than 10 meter, I don't know, 7 or 8 meter drop. So really high, both severity and likelihood. And we had to do this piece of work and we had to say, well, what do we do? Do we seek to reduce the severity or do we seek to reduce the likelihood? And we determined, well, actually, there's not a lot we can do to reduce the severity, because if you come off that roof, you are always going to fall 7 meters. We can't reduce the height of the building. We can't add crash mats, bouncy castles, trampolines at the base of it. There's nothing there we can do reasonably. So we have to put a lot more effort into reducing the likelihood, which was by installing edge protection, putting the barriers in, some lighting, some signage. We actually delineated on the ground or on the roof structure exactly where to walk and put emergency lighting in like you would do on an aircraft. So it's at low level, not high level. So in that case, by using a risk-based approach, we said, well, which one can we do? What can we have an impact over? We can't change the severity. We can, however, change the likelihood. And that's a really common approach, not under Article 9 of the fire safety order, as we would do, where we're going and unwedging doors and looking at latent risks, but in the design of buildings as well. What can we do? Can we reduce severity? Can we reduce likelihood? And we make decisions based off of that. A couple of quick examples. This is a report I sent to Sean, and over breakfast the other day, he pulled apart. But in the spirit of what we were talking about, which is what is true risk assessment, here is an executive summary from a report. We've broken down, this is a section, a small snippet from a much larger report, of course. We were saying the summary table provides the guidance for hazards and ignition sources. What is the risk associated with that? Is it low, moderate, high, or extremely high? Similarly, for means of escape, indicate appropriate overall risk level, moderate in this case, and emergency lighting was low. Anything we've got in there that is high or extremely high, we put in place an action plan. So we say if we had an extremely high hazard, let's use the roof as an example. If that was a part of a risk assessment we were carrying out as part of that regular check that we do in all buildings, we would say there's a high consequence and a high likelihood that you will get injury, fatality, otherwise consequential impact from that means of escape you've got in place. That might be intolerable. So we would say, okay, let's reduce one or the other. In that case, it's reducing the probability, not the severity. So as a quick introduction for fire risk assessment there, we're talking about our legal duty we have in buildings once they're occupied and once they're managed. We also do that during the construction phase. So we have construction fire risk assessments, but also during the design, we make decisions based off of risk as well. And talking a bit more about risk of fire, I popped this in during the break because we were talking about it this morning. I wanted to just quickly do a couple of slides about this before I go on to the point about structures I want to make for the bulk of the rest of the talk. I mentioned this earlier, A set, R set, and for anyone that wasn't in, this was in a discussion about how we make decisions really for existing buildings, but we do use it for new build as well. This is the methodology for how we design a means of escape. And as a graph, it looks a little bit intense, but actually it's really straightforward. Across the top there, we have our available safe escape time, our A set, and we calculate that by working out the point at which conditions are no longer tenable in the building. And that loss of tenability might be because of a structural collapse. The building itself is no longer supported and the building has failed. Or it could be because temperatures throughout the compartment are too high, they're no longer tenable, and it's no longer conducive to human life. It could be because toxicity is too high. It could be because visibility is too low. Whatever we determine as being the limiting factor in a fire is the time at which we can no longer escape, and that's our A set. So that's along the top. Along the bottom, we have the means of escape phase broken down into lots of different stages. And it's broadly broken into 4. So we start with the detection time, then the alarm time, pre-movement, and then travel time. And this is where we do lots of design work based on risk here. So our detection time is the time from which the fire starts to the detector activating, whether that's a call point being activated, if it's an automatic detector, if it's somebody physically seeing the fire. We then have a delay between that happening and the entire building being alerted. Now, that might be quite a short period. We usually add in 5 or 10 seconds system lag if it's for an automatic system. It could be 6, 7, 8 minutes if it's an investigation period. Could be even longer if we've got stay put and progressive horizontal evacuations, for example. The pre-movement time is the time it takes for somebody to decide to start to evacuate. So that's anything from wayfinding if they can't find an exit, tackling the fire themselves, collecting their belongings, getting the kids and the cat and getting out of the building. And travel time is the time from which they begin moving to the point they leave the building. And in a design and in a risk assessment as well, we seek to quantify these things. So we try to calculate the time to escape, which is the R set, by adding up all of those different components. And we compare that to the available safe escape time. In essence, what we're doing is, for the escape time, we're adding up each component of the means of escape, summing them together, and that gives us our total time to get out of the building, and comparing that to what are the conditions at that point. First of all, is the building still standing? Secondly, what are the temperatures, the toxicity, the visibility? Is it still conducive for people to be in the building? And if it's not, that's where we do our design work. Because in here, what we might choose to do is say, it takes too long for people to evacuate. So what we're going to do is reduce something down. Let's try and reduce down the detection time, put in additional detectors, or reduce down the travel time. Let's put some compartmentation in, put in additional firewalls. It means once you reach that point, you're in a place of safety rather than having to get to the front door. Let's enclose that open stair because that's not safe, and we want to stop counting travel distance once we reach there. So this A set R set is picking up from a point we made earlier more so than anything, but it's a really important tool for us in fire that I like to tell other disciplines about, to say this is how we're making decisions about design for means of escape and for tenability. The application of this is what I've just said, and I've highlighted the word or put in bold the word appropriate. I'm going back to our functional requirement, which is we always have to determine that we have provide appropriate means of warning and appropriate means of escape as well. So this is a methodology that we use in the design of new buildings and also the review of existing buildings. It's detailed in one of our published documents, 7974. So PD 7974 Part 6 gives us this methodology, and we use it in large complex buildings, or those that are complex for not necessarily because of the building itself, but existing condition, existing defects, latent defects or latent hazards that we can't otherwise mitigate. We might use some of this performance-based design principle. So that was picking up on something we talked about earlier, and I want to pick up now. These are a couple of slides I've added in for the next few slides about something we talked about earlier to do with structural engineering and a point we made about periods of fire resistance. And it allows me to talk a little bit about fire science, not in too much depth. I appreciate this is a high-level CPD, so we're not doing too much learning here, but hopefully some useful points anyway. So, stages of fire growth. When we talk about fire, when we consider the risk of fire in a building and we consider what a fire might do, we look at a number of different things. We look at the people we're trying to protect. What's their occupant condition? Are they awake? Are they asleep? Familiar with the building? Unfamiliar? Any cognitive impairments, anything that we might need to consider in designing that space for those people. We also look at the building environment itself. So we consider what's the height of the building, the biggest compartment, what's the fuel source, what is the ambient condition, is it in a basement, is it ventilated, etc., etc. And the third thing we consider is the fire itself. And this is back to my spider diagram at the beginning, some of the chemistry and physics coming in and some of the actual science. And we look at something like this. This is a fire growth curve. This is a prediction of what a fire might do. And we usually plot these things against time, down at the bottom there, against some parameter of the fire. So the heat release rate, in this case, the HRR, or the temperature of the fire, or any other component, the mass loss rate of the fuel, the toxic output, whatever it might be. And we break the fire down into a series of stages, as shown on the graph. So all fires have an ignition, sometimes known as incipient phase. There's then a growth phase until it reaches its peak heat release, the upper limit, which we call flashover, which is a transition to a fully developed fire, and then it will decay. And we usually plot it on a graph that looks something like this. And I'm going to come on and talk about fire resistance because it's important for us when we're working alongside our structural engineers in industry. And what I want to do is overlay on the graph, as I've done here, what we're interested in terms of fire and fire resistance, especially at different stages of this curve. Because we have two different types of fire testing and ways of classifying materials. The first one is called reaction to fire. And that in blue on the graph is the contribution of all the materials to that fire as it grows. And when we talked earlier, we know about our internal linings requirement is one of our legal duties under B2 of the building regulations. We said we're interested in what contribution do those materials make to the growing fire. That's our reaction to fire classification. That's class A1, A2, class B, C, D, E, and F under the Euro class now. But once that fire, or once that that element of structure, once that column or that door or whatever it might be is exposed to a fully developed fire, we start the clock essentially. We say, okay, well now we're interested in fire resistance. For how long does that member maintain its function? For how long does it hold up the floor, or does the door remain solid without letting fire and smoke through? What's that period of fire resistance? And that's when we talked earlier about 30 minutes, 60 minutes, 90 minutes. It's that second part of the graph. It's how long does it withhold during the fully developed stage of a fire, and actually some of the growth as well, but predominantly it's once that fire has started. So I'm going to pick up on this because I really want to touch on fire resistance now for the next few slides. Reaction to fire applies during the early stages of the fire, an internal lining material with a class B property. And fire resistance is how effective the material is at performing its function when exposed to the fire. For example, a structural column with 60 minutes fire resistance. And a question we had earlier on today was about at what point do we determine, or would a fire engineer determine whether we need to have 60 minutes? Well, we determine that at design stage, or we can go to an existing building and give that requirement. And what we're interested in is where that structural member is being attacked from. So if it's a floor, we're interested in the fire coming from below. So we would put the fireboard on the underside. We'd underdraw the underside of the material, because what we're saying is when it's exposed to the fire, we want 60 minutes fire resistance for that material to be in place. Now, here's where it gets a bit complicated, or at least a bit trickier, shall we say, for us in fire engineering. Fires themselves are very difficult to predict. We can't really run numbers and accurately predict what will happen in a fire. And I've done this experiment myself. If you build a room, build a living room and set fire to it and measure everything that's going to happen, you'll get a time at which the fire transitions to flashover, the temperature at the doorway, the visibility decreases to X, Y, Z, and you get a load of results, quantifiable results. And if you strip that room out and build it exactly the same way again, with the same furniture in the same place, ignite it in the same way, you don't get the same results. I would say it'd be almost impossible to get the exact same results, but you actually get quite a lot of variance. It's very difficult for us to make accurate predictions about fires, how they'll grow and how they'll spread. There are just too many things. The three things I talked about, the building environment, the people in there, and the fire properties themselves, each one of those is a variable, and each one has loads of sub-variables as well. So very difficult to predict what will happen in a fire. Think about if we're doing a risk-based design, we're trying to think, okay, what's the risk of a fire in this building? Even if we can quantify that, it's difficult to know what will then happen. But we do have to make those predictions as fire engineers. It's our job to predict a fire in a building and see what we can design in to try and mitigate, to try and protect it. So we have a series of standard fire curves that look something like this. So on the graph on the right-hand side there is a series of what we call standard fires, and the standard fire curve, in fact, is the thick black line there, which is in ISO 834, and we'll probably be familiar with in structures as well. Certainly in fire, we're familiar with this curve. It starts at 0. There's a growth phase. It's actually a logarithm, so it never decreases. It just reduces the rate at which it increases over time. We call that the standard fire curve, or the ISO 834 curve. And we have different variants of that for different types of fire. So in a tunnel, we have a slightly different fire dynamic. We anticipate it will grow quicker, but it will cap itself and it will reduce. The external fire curve does something similar. Hydrocarbon curve, if we're working in oil and gas, increases and reaches a steady state, doesn't keep growing. So we have these different variations of a design fire. The one I want to concentrate on now is that black line, the ISO 834. Otherwise known as the standard fire curve. It's a really important principle I teach to students on the degree multiple times, because this is essential knowledge for, I believe, outside of fire engineering as well, because it's a really important principle that comes from it. That curve doesn't look anything like that curve there. It doesn't have the growth, the flashover, and the decrease. So it is a kind of idealized version of a fire. And if we look at what happens in a real fire, it doesn't look anything like that either. We can look at, I'm going to skip this slide and just go on to the graph itself because it describes it better. In that document I just had on screen there, they did a series of tests of living rooms and prison cells and buses and all sorts of things. And this is real data from fires that was being monitored. This is a living room fire. This is what we expect to happen. In this particular case, they ran the test for 7 minutes, at which point the curtains were ignited. Slight decrease in heat release at 8 minutes, and then it increased, then it flashed over at 11 and died down and went back up again. I dare say if you stripped all the materials out, redid it, you get a totally different graph. But this nonetheless is the graph of a real fire. So this is a real fire test of a real living room built to simulate what could happen in a real fire. And there's a couple of things on there we can pull out. I won't do it in full detail, but note on the left-hand side there that the peak heat release is 5,000 kilowatts or 5 megawatts. So quite a significant fire that's occurred. And if instead of doing a living room, we do a prison cell, as was done here, we see we get another curve again. Looking to that number on the left-hand side, instead of being 5 megawatt this time, it's 2.5. We could say that a prison fire is half the severity, at least in terms of peak heat release, than a living room fire is. But we can't draw many other parallels. Neither of the graphs are smooth. We don't have the nice smooth curve like we have in our standard fire curve that we looked at, the ISO 834. We have a decay phase for the living room fire, but in this case, they've had to intervene and put the fire out, so we don't have a full data set. And this fire test ran for 30 minutes. Would we expect 30 minutes in a real fire? Would someone intervene? Would we get the fire service there in that time? So these are all just predictions that we're making and data that we're collecting. Now, one thing I'll just note before the next slide, before I move on, down at the bottom, this is in a period of minutes. So we've got a 30-minute fire test for the prison cell. Christmas trees highlight a really interesting point. The main thing of interest to me is they've changed the scale from minutes to seconds. And this is what we get from Christmas tree fire tests. I like this graph a lot, actually, because they plotted 4 different tests on the same graph, and it's the same materials being tested. You see that you get this variation. But the worst case of those, plotted in green, takes us up to 5 megawatt again, which is the exact same heat release rate as we had for the entire living room, this time just from one Christmas tree. And it's achieved it in 50 seconds, not a period of minutes, less than a minute. You get the same heat release from a single Christmas tree than you do for the whole living room. Now, why is that of interest here when we're talking about risk assessment? Well, these are changing and variable fuel loads we have in buildings. You could say that if you bring a Christmas tree, and this, it's worth noting, are live Christmas trees you cut down and they dry out, and you get that really high combustibility of them as they wilt. That's a totally different fuel load to what we might design. If we design a living room, well, in fact, we would. Let's design a living room for a residential apartment. We assume that that's got a peak heat release of 5 megawatt, but we're not designing it in December. So we're not designing it for that variable fuel load we have in there, which is another complexity for us when we're designing a reasonable design fire case scenario. We have to consider what is the worst case and how will it change? What's the variation we might have? So looking at these graphs, we've got these curves. None of them are smooth. They're all jagged, and we run the same test multiple times. We don't get the same results. Okay, so the point up to this point here is that it's very difficult to predict fires. Even if we do probabilistic risk and we say what's the likelihood of a fire occurring, everything that happens thereafter is based on loads of variables and very difficult. But we do have to, in some cases, make these predictions in our designs, or particularly, I'm going to harbour the point here because I think it's a nice way of demonstrating it, in fire testing. So if we're doing standardized testing, we're comparing one thing against another, we have to have a standard fire curve, which is why we call it standard fire curve. If we have 2 doors manufactured by manufacturer A and manufacturer B, we want to ensure a fair test for both of those manufacturers. If I was manufacturer A, I want to know that the other person is being tested to the same standards I am. So all of our fire tests and all of our structural fire tests and all our products are tested against the same curve, and it's that one on the right-hand side. Hopefully we can see that that doesn't look like any of our real fires we've just seen. It doesn't look like the Christmas tree, the prison, the living room, or the initial stage with the decay phase at the end as well, and the flashover. Used widely in fire testing, and I'm going to do this super quick because I've run over on time because I started slightly late, but fire doors is a nice way of demonstrating this. If we've got a fire door going into a building, we say it's a 30-minute fire door or a 60-minute or 90-minute, exactly the same as an element of structure. The fire door itself means, what that means is when we put it through the test, it's lasted 30 minutes. So we've tested it under the furnace, we've tested it to that fire curve, and at 30 minutes it's failed, or at least in less than 60 minutes, which means we've only accredited it as a half-hour fire door. It means that in the event of a fire, and if it's subjected to the same fire, it lasts for 30 minutes as well. And for a fire door itself, we test the entire assembly, not just the door itself, but the hinges, the frame it sits within, any ironmongery that's on there, the self-closing device, any glazing, the door leaf itself as well, etc. Big issue for us if we go to a building and we can't confirm that the door hasn't been tampered with. They haven't changed the hinges, they haven't changed the glazing out, any of that, because it's tested as a whole unit. And the way that we do test it is like this. We put it in a furnace, and that furnace exposes it to temperature from one side. So on the image on the screen there, that's the British Standard furnace, the 476 Part 20. You put the doors into the frame, into the swing arm. From one side, it's exposed to temperature. That simulates a fire in one room only. So the door, we anticipate a fire door would only be attacked from one side if it's closed properly. And what it simulates is that the fire is growing on one side and it's subjecting the door on just the one side only, on what we call the exposed side, to elevated temperature. And we do that against that curve so that if we do the test again, we in theory get the same result. We accept there'll be a slight error percentage, a few percent here and there, but broadly, we're testing it for how it will be installed in a building. And it looks something like this. You usually test two doors at once. It's often the same door hung in both directions, so you can see which one is a limiting factor. It's usually the one where the hinge is exposed is the one that fails first, as you would expect. And it's installed as per its final condition. Okay, we're testing this at this point to simulate what would happen in the event of a fire just on the one side. What we're testing very quickly, again, we're not really touching on this too much. I just wanted to get to the point that I'm going to end on shortly, is the integrity failure of the door is when we get sustained flaming through the door, or some of our gap gauges, so we look for gaps in the fire door, if they can penetrate through, and then we demonstrate that we've lost the integrity of the door, so it has failed. If it was a structural column or a structural beam, we would test it to the curve, expose it from the underside, and we'd put load on it, and the point at which it can no longer support that load, it's failed its function and the test ends. Exactly the same principle. The same we would do for a piece of ductwork or fire stopping or a fire door, whatever it is. We're testing it in a real fire scenario against that standard curve, and we're seeing at what point it fails. But here is a really important consideration. It's one of the most important lessons for fire engineers that I teach on the degree. It's one of the most important things I want to give out from fire engineering to other people as well. It's very difficult to predict a real fire. And when we do these tests and when we make predictions, they are usually idealized. We are assuming it will do certain things, but we know that if we run the same test twice in a real lab, we don't get the same result. So we're having to make assumptions. We're having to make some simplifications. And that standard fire curve is based on cellulosic materials. Timber pallets actually is where it comes from, research that was done decades ago. And a real fire might be more severe than what it's been tested to, or it might be less severe. It's very unlikely to be exactly the same. So if a component, such as a structural column or a structural beam, lasts 60 minutes in the standard fire test, what that means is it's been tested to that standard curve, but the real fire is likely to be, in fact, it almost definitely will be, very different condition. And I'm going to finish on this because there's a really important takeaway from that, and it picked up on a question we had this morning, which is why I want to give it. And it's called the equal area hypothesis, given by Ingberg, who was a fire scientist. So, severity of a fire is not just what's the temperature of the fire, because throughout that curve, it changes. So at point 1 or point 0, its ambient temperature might be 20 degrees C. At point 1, which is the peak of the fire, it might be 1200 degrees C. So you can't just pick a point on that graph and say that's what the severity of the fire is. The way that we do it is we measure the area underneath the graph, because what that gives you is the severity in terms of how intense the fire is and for how long the component was subjected to that intensity for. So it means if there's a variation, it means if the graph increases and decreases as well, you get this equal severity between the two. And if we compare two areas under the graph and they're the same, we assume there's an equal severity to the fire. So the takeaway point, why that's important. Why do we care, Joe? Well, if we've lasted 60 minutes in the standard fire curve and we've got a 60-minute column, it means that when a real fire reaches the same severity as what it's been subjected to in the test, it will fail. So on the graph on the right-hand side, we've got the curve, the standard fire curve, and we've got two dashed curves as well, fire A and fire B. Fire B is the one at the bottom, which is the kind of shorter dashes. And in there, you can see that that real fire is less severe than the standard fire. So that 60-minute column will last far longer. It will last maybe 90 minutes in that fire condition. So when we were talking earlier about, would we get to a point where we'd say to the fire service, don't enter the building because it's about to collapse? Well, You'd be very good to calculate off the top of your head, but in theory you could do that. You'd have to know how severe the fire has been. Fire B, we'd be okay because our 60-minute column is going to last longer than 60 minutes. But look at fire A for a second. So fire A are the longer dashes, and we can see what happens is in that real fire, it grows more quickly than the standard fire curve, and it reaches a higher temperature quicker. It then decreases. But in the early stage of the fire, it's more severe. So what that means is that our 60-minute column or our 60-minute beam or 30-minute door, stick with 60 minutes, 60-minute door will not last for 60 minutes in a real fire. You can have collapse of a building far sooner than what it's been tested for if the real fire is more severe than the standard fire test curve. And that is a really, really important consideration, because what we see an awful lot in industry and what we get as an assumption is if we've got 60-minute protection to the structure, we've got 60 minutes to get people out. We'll keep people in the building for 50 minutes and then start to evacuate. Not the case at all. What could happen is that the whole building could collapse far sooner than that. The World Trade Center's example we gave earlier, far more severe fire than what the material components have been tested to, and consequential collapse. Of course, there was damage to the structure as well, so that's not an idealized scenario, but the theory holds. If in this example here, we've got the TS, which is the standard test curve, and TR real, it means that the areas under the graph are equal far sooner than 60 minutes, and you would get that loss of that building in less than an hour. So fire severity is a really important principle for us. And when we're doing our fire risk assessments and when we're doing our fire strategy design, it's really important that we make suitable assumptions as to what size of fire we might get in that space. One of the reasons it's very difficult to do. Fire risk assessments are very difficult, and particularly when we do them properly and do them in design work, we have to make lots of assumptions and back them up as best we can. So to finish on, just on that point, here's some things I've collected over the years of things that are incorrect, things that people have said, and it's either students writing assignments or it's colleagues in industry that I've seen, peer reviews that I've done, of things that we shouldn't accept, where people have taken this notional figure, this X number of minutes up to the column, X number of minutes to the door, X number of minutes to the ductwork, and read it as standard. So here's something that I read in a real fire strategy. We had a 2-hour firefighting shaft, and it picks up on the question from this morning. What they had said in there is after 1 hour and 50 minutes, we'll raise a second alarm to tell the fire service to evacuate and leave the building, because they've only got 10 minutes left is the inference. But the building is never going to collapse at exactly 120 minutes. It could collapse after 10 minutes if the fire is more severe. If the fire is less severe than the standard test curve, it might last for 10 hours. Building users are safe to remain in the building for up to 1 hour. Not the case at all. I mean, it could be that they're safe for 10 minutes. It could be they're safe for 3 hours. Depends on the fire that's happening. We have to do a series of analysis to work out what's the reasonable worst case fire and compare that to the standard curve if we want to do that analysis. It's safe to remain in the building for up to 2 hours in a fire. I mean, it might be the case, but not just by virtue of the fact you've got 2-hour incandescent spray on the steels. And the ASET, the available safe time, is 90 minutes, something I read in a peer review that I was doing of someone else's work. Just an incorrect assumption, something in fire science that simply doesn't hold up. Highlighting the point, it's really important that in fire safety, we really consider the chemistry of the fire. Highlighting again my point, I hope, about us having to understand lots of different disciplines. If I didn't know about fire and I picked up approved document B and read 90 minutes for the structure, I accept it's not unreasonable to say, okay, we've got 90 minutes to get people out of that building, because that is the way it reads. But by studying and understanding fire, we know actually that's not the case, and it highlights some of the complexities we have in fire strategy design and fire risk assessment. View. Okay, sorry, I had to speed up, Sean, because I started a bit late, so I'm not sure how we are for time and questions, but you've got 4 minutes till you're on, so we can kill 4 minutes for some questions if there are any.
Yeah, no, so I saw a few come through. Thanks for that. It's really, I got a slight headache from it. I still hate portions of it, but yeah, it was really interesting digging into the bits you added on as well at the end. There were a few questions come through, so I'll dig on them. I did write a few down. There's a few that come through I wasn't quite sure about that I was following. So I think, let me just check. Andrew and Thomas were arguing about the abbreviations for regulatory reform order. Apparently there's a million of them, but I think they sorted that out between themselves.
I can guess what the argument was. It's an ongoing argument in the industry, yeah.
Okay. Mike chipped in with, what are your thoughts on people, organisations that challenge the actions you've recorded on your fire risk assessments for their buildings, as they do not want their governance groups or similar to see a higher number of what they deemed as unnecessary actions, although your assessment has determined the actions as being necessary? So basically, if you stick it in as high and they want it to be a medium, which is the crux of why I don't like your risk assessments, by the way.
Yeah.
It's subjective. There's nothing measurable there.
Yeah.
And that's why I think you could give one answer and I can follow your reasoning now. I get where you come from, but you've still got to pick where you lie on that square. And you could pick one square and the next engineer across could pick something else.
Yeah, absolutely. I mean, in response to the question, I say to the client, what are you paying me for? If you have an answer in mind, why am I here? It's the similar, if you go and do a risk assessment and you say there's a door wedged open and they unwedge it and say that doesn't need to go in the report, does it? And I go, well, yes, actually, it was a risk. Admittedly, you fixed it immediately, but I'm here to give you that snapshot whilst you're here. So I suppose I don't like being led by a client, in answer to was it Mike's question you said?
Yeah.
But I do agree entirely that it is subjective, and that where that comes from is the quality of the report that's being produced, the quality of the assessor, and how well they can back up what they're saying, in my opinion. For me, it comes from how good you sort of back of house is and how you justify that yourself, how you, because the guidance is slightly lax in this area, you have to quantify it yourself and say, what is it we deem to be high risk? But even if you had it really well quantified, it's subjective to the building itself. Because you could say that if you've got a door that's wedged open to a stair, it's less consequential if there's two stairs in the building. Not to suggest it's okay, but the consequence of that is specific to that building arrangement. Excuse me, sorry. So yeah, it's fair point.
Cool. Someone raised the point of lithium-ion batteries when you were talking about your fire curves and where they fall on the curve as well. And how would an FD30s stand up? So the full question is, add lithium-ion batteries failure to the list. How would an FD30S stand up? Not as we would want. Over my head, that one. Sorry.
No, I'm not as we want is the correct answer, in my opinion. I mean, what happens is if you get a lithium-ion battery, so I'm doing loads of work on lithium-ion at the moment. I'm actually doing a shameless plug coming up, Sean. Look out for this one. I'm doing a webinar for IOSH soon about lithium-ion batteries. So what happens is you get a really fast-growing fire. If you've seen videos of car fires and Teslas going up, you've probably seen it. Really high growth rate, okay? Even if the heat release rate is the same, you've got that difference in growth rate. So your 30-minute door that you've got to your garage, if it's a lithium-ion battery that goes up, or if it's a car fire, electric vehicle fire, won't last 30 minutes as it did in the test, because it's a more severe fire. So yeah, that's exactly the kind of risk we identify when we think about design fires. It's a really good example of, actually.
Can I just quickly, John, if you've joined in, added the call already, do me a favor, just drop a comment in the chat and then I'll sort you out for the next session. I'll change your mic and stuff as well coming up. Because you started late, a couple more questions.
Yeah,
we'll pinch 5 minutes if that's all right. Someone said, so in design, should we, sorry, this was Martin. So in design, should we not assume or assess that fire resisting doors, walls, etc. would fail, say, 30% of the time? Therefore, fire spread beyond the enclosure and greater consequence to occupant safety. So do you follow that one?
Yeah, I think so. So if we have a failure rate of the doors, now we don't tend to do that in the design. Actually, what we do, doors are a slightly interesting case because there's a risk of those being open because they're openable. John's on, Sean, I've just noticed. A door can be left open, be wedged open. There's a higher chance that they will be left open. In fact, in our guidance, it says in houses, 20-minute doors that you have to all rooms will prevent the fire from spreading. But of course, forgive me for saying this in a public forum, but I don't close the doors in my house at night. I close the one maybe to the kitchen, but like otherwise the cat can't get to his food. So I don't close my doors. So we look at the risk of something being wedged open. And do you know what? In a house design, I would assume, okay, I'm not going to rely on that door being closed because I know the way that people use buildings. Same with doors in hospitals. I was looking at a hospital the other day with some of my colleagues who I think are on the call. I know that those hospital doors are going to get absolutely mullered by beds and trolleys every day, and they're going to be damaged really quickly. So yeah, we do consider that in the design. There is sort of no point, or at least I wouldn't say no point, but it's far more consequential to say the door between a back of house and front of house in a restaurant or shop needs to be fire rated, because they're going to wedge it open because they're going to be bringing deliveries in. So we do consider the use case of it, and it's all to do with how people use buildings. Big part of probabilistic risk for us is how people are actually going to use these sites that we're designing.
Can I ask one more question if that's all right? You talked about prison cells earlier.
Mm.
Do you guys consider the construction? I know you consider the linings and the combustibility of that, but do you consider, you talked about external shielding earlier, or radiation shielding to the external face earlier. So is there different buildings or different size rooms or different constructions where you're getting an increase in temperature just to how it's formed, how it's constructed? How much does that play a part on risk assessment?
Yeah, massively. I mean, prison cells is a great one because they're built of concrete usually, so nice big thick walls. So you assume the fire is going to be contained regardless. So if we need something like, we might get 60-minute structure needed, and if it's a concrete wall, we'd say given a certain thickness, it's going to give us 60 minutes anyway. So we don't need that proprietary fireboarding on. I've just had, for example, what was the example I was looking at? Timber floor, and we've been asked to do a charring calculation of what's the inherent fire resistance of the timber. So timber itself forms a char layer, protects the inner core. If you oversize the timber structurally, you can give yourself the fire resistance without painting it, spraying it, encapsulating it, or anything like that. So yes, absolutely, we look at the inherent properties. If we have something like a structural steel and we encapsulate it in 60 minutes fireboard and the fireboard fails, we then have the inherent properties of the steel. So we don't lose it at the 60-minute point. We then have the properties of the steel as well, as long as it doesn't weaken and stop performing its function. So yeah, we can cumulatively give ourselves the benefit of different materials together and rely on, one of the biggest tricks we do in fire engineering is hotel rooms. So hotel room build-ups, often for acoustics, give us the required fire rating. It's there anyway, so we review that detail and say, well, because you put an extra boarding in, an acoustic mineral wool in there, what does that give us? And you can calculate that. You can say it will give us an enhancement between rooms.
Look, when you talked about charring of timber, we do that calc as well as structural engineers. So we will oversize it, we'll work out the charring and make sure, and for us, that's an accidental consideration. Are we doubling up the work in the design process then? So are you doing the same work we are? So for instance, for concrete, steel, timber, masonry, part 2 of each one of those codes is fire that we should be considering. And without making more work for myself, I wonder if that's a chat we have. Maybe this is pointing us that way next.
Yeah. Well, that's really interesting, okay, because it's not something that we're often asked to do. So it's usually, so in a fire strategy and a design, we'd say you need 60 minutes or 90-minute structure. And only in rare cases or in existing buildings are we asked to do that detailed calculation. At least that's my experience from my professional work. But it's something we're perfectly capable of, and I think ought to input into, because we can give the parameters of what the fire is that we've designed into the building. Or actually, when I do it, usually if I'm doing it, I reverse engineer it. So I think, again, I'm working on existing buildings a lot of the minute. Existing building, this is what we've got. Let's reverse engineer it and say, what's the worst case fire it can withstand? Then I start to design my room and say, do you know what? You can't put a kitchen here because the fire's just going to be too big. Make sure that this is the bedroom or living room or something like that. So yeah, potentially we are, but I think it's one of those where we should be working together on that, right? Structures and fire, because we should input the fire parameters. You guys do the specification of it. And that's a nice element of the collaboration thing that we're probably, maybe we are doubling up. I don't know, but we should certainly be collaborating on it. Yeah, definitely.
All right, we'll add it to the workload. All right, thanks, Joe. It's appreciated.
Brill, thank you.
John, I've added you as a presenter, so you should be able to share your screen.
Do I do that? Is that it's top right hand corner share? Is that
that's
right?
the one.
Okay, and choose want to share. Right. All right, I'm not sure how to find. Let me put up the.
So it should be share. I think it's screen, and then it should just kick you straight into whatever you're looking at.
Yeah, oh, share. I'm with you. Right, share. And then.
There you go.
Is that coming up?
Yeah, we can see it.
Has the slide come up?
Yeah, if you just click your slideshow, you're ready to go.
Right. Okay. So that's all okay, is it?
Yeah.
Lovely.
Right.
Okay. Well, thank you. Sean, for giving me these few minutes just to interject really and to put a slightly different slant on this. We know that, I guess, this is the biggest shake-up of building legislation in several decades, and I guess for many people watching today, it will be the biggest shake-up in their career. And understandably, the higher risk buildings are sort of hogging the limelight a bit, and yet in reality, they represent the minority of structures. And of course, we know that the Act applies to all structures from the modest, what I call the high street project, right up to the majors, which might actually be more complex, bigger, and difficult than a building which actually is formally registered as a higher risk building, and everything in between. Some of you may have seen the very recent 3-series programs on BBC about the Columbia shuttle disaster. And I guess that probably everybody here, almost everybody, has seen the 4-part series on the post office debacle. And indeed, these, together with other past examples, both inside the industry and outside it, highlight that there are common features to them all. Remarkably, the root causes tend to be the same. And two features. One is they are well known, very rare to get a failure in any circumstance where the cause is not known. And the second characteristic is that despite knowing about them, no action was taken. No effective action was taken. A phrase I came across the other day, in fact, it was on LinkedIn, was willful blindness. And that is a pretty good summary. And my concern is that in concentrating on the Building Safety Act and how we comply with it, important though that is, of course, we risk repeating these root causes in the future. And I've designated these as soft hazards, and they appear on all projects of all sizes, not only buildings, but also civil engineering structures as well. And we're not just interested here in life and limb. Of course, that comes top of our list, of course, but we're also interested in when things go wrong because of PI claims, delay, and reputational damage. So we're interested across the whole gamut of this. So what are soft hazards? Well, the definition I've given them, something that has the potential to cause harm. Well, we all know that is the definition of a hazard. Originating as part of the design process, importantly, but which does not result in a work activity on site. Now, we're all familiar for the last, 29 years of CDM, but that has been presented for the whole of that period, by and large, as what I call hazards within HSE's comfort zone. That is work at height, manual handling, noise, and things of that ilk. What it hasn't included are what I call the soft hazards. And that has left a major gap in our understanding and action on these important issues. And I've given just some examples here of soft hazards. A failure to check. Clearly that has a structural safety implication. Lack of management and oversight. Inappropriate use of software, i.e. failing to check the assumptions in the software or that it is validated for the use intended. Site supervision is a major issue. We know that over the decades, it's been reduced from a definable adequate level down to almost nothing at all. Early mistakes being made in the concept, which get more difficult to deal with, as we know, as design progresses, and poor submissions to building control under Part A. So this is where the major risks lie, and ironically, it's where areas where we have avoided, we have ignored that in the past. I've written a checklist which is the document highlighted at the bottom of the slide, which is available there, and that it's not definitive, but it lists the major, most common root causes, and the philosophy in the checklist is that you should be complying with these unless there's good reason not to, in which case you need to say why. So Sean, I hope that link can be made available in some way after the event, if that was possible.
Yeah, I'll throw it in the chat as well.
Good. Okay. Now, industry, the only body that has tackled these, to my knowledge, is SPHStructures, the Standing Committee on Structural Safety. I'm not aware of anyone else really homing in on these to the degree necessary. I'd just like to mention the 3 Ps before we progress any further. This is a really useful, simple, and remarkably accurate way of thinking about how things go wrong. We've got to get the right attributes to the people we use. We're familiar with that, competency and resource. It's the processes that we need to keep our eye on. And I've just given some examples there. It's very rare in the UK to get a product failure. Over my career span, we have had a few, I'd say 4 or 5, maybe possibly 6, but it's quite rare. The main concentration needs to be on people and process, but without taking our eye off the ball, of course. And I can't go much further without mentioning Grenfell itself, because of course this is where it all started. And it's not time today to go back in any detail other than here, these 2 slides. First of all, to remind ourselves of what Dame Judith Hackett said at a talk about we needed to move from a position where it won't happen to us, it happens to other people, to a position of chronic unease, which is where if we haven't taken any action, realistically, we ought to be honest and say that is where we really are. We should be in a position of chronic unease with regard to the way in which we work currently. I studied the Grenfell tragedy in quite some detail over a period of years, and I'm still doing it. I'm still involved. I've listened into much of the evidence on the inquiry, and no surprise, if we leave aside deceit and possible criminal actions, the lessons that come out of here are ones we all knew about. There is nothing new at all. They have occurred before, and they are entirely predictable. And you'll see the points, I'm sure, just by looking at this slide. Novation, very common feature in building work. The essential need for clarity when moving across from one client to another. Clarity of brief. Is your brief absolutely clear on what you are going to do and what you're not going to do? And is that being made aware to other relevant members of the design team? The relevant expertise in the field in which you have found yourself on this project, which might crop up maybe unexpectedly. In the past, a number of structural engineering colleagues have relied on building control as a checking mechanism, which is entirely inappropriate, incorrect, and certainly under the Building Safety Act, it would not wash. But that's something we've got to get out of the habit of. The designer is responsible for compliance and not building control. Understanding technical issues, of course, completion of design by others, a frequent occurrence in building structures, not always for the right reasons, but that's where we are at the moment. And if that's the case, we need to make sure it is absolutely clear to those following what the assumptions have been in the design, how far it's got, the codes that have been used, and so on. And that information is passed on so it gets to the future designers that may follow on months later. Clarity of responsibility, these are all linked to some extent. So, for example, who is responsible for the design of the balcony fixings or the cladding fixings? Is that absolutely clear? And in the contractor package, if they are responsible, is it a design and build package as it should be? minor items can often cause the most problem. They may not cost each other on a unit basis, but if they repeat, that can be a major issue and needs absolute clarity for the same reason. Think Boston Big Dig Tunnel, where one fixing caused hundreds of millions of pounds worth of consequential cost. Change control, again, and site supervision, I've mentioned on a previous slide. All these need to be with absolute clarity, and they did not have that clarity on Grenfell. We also need to remember, and we're not good at this, or we haven't been good at this, that there is guidance produced by our peers on various aspects, and we should be following this unless there is really good reason not to do so, and that is recorded. So often in the past, I found people are either totally unaware of this guidance or have chosen not to follow it, and that is simply not acceptable. And I've just given some examples here. There are, of course, others. The site hoarding guide. A full height hoarding, solid hoarding, is a dangerous structure if not designed properly. And the Temporary Works Forum has produced a design guide, and one would expect that to be designed to that. Just as an example. So there are lots of others of these, but they've been produced by peers, experts in their field, and they should be followed and adopted where they are relevant without further ado. We do need more to take out ambiguity. So summarizing then, because this is just a very short piece, we've got good old CDM, very well known now, of course, still often poorly dealt with. But that's not the subject of today, and I don't want to get into that. We're concerned with these soft hazards, some examples of which I've given, and how they sit with the Building Safety Act, which of course we are going to be concentrating on, but without forgetting the soft hazards behind them. So last slide, Sean, just to leave with you for later, two references. One is the book, which I did write, but I make no apologies about pushing that. And the soft guide I've mentioned before, which I would hope that I think there are about just under 60 people listening in or watching this afternoon. I would hope that every one of you, if you haven't already done it, would download that soft guide, even if it's just a comment, but just so that you are aware of it. Thank you, Sean.
That's great. Thanks, John. Just appreciate your time.
Do I stop sharing now?
Yeah, I'll nick the screen off you. No bother. If you can just mute your mic, and I'll take over. I'll tell you what. I'll take you off. There you go. Yeah, you're muted. Okay. Right, guys. I'm just going to reiterate quickly soft hazards. So this is the document. A few people have thrown it up in the chat. Thanks for that. When I read this for me summarizes all the niggly arguments you have through a design process. It's all the stuff about interfaces and whose responsibility is whose, and people don't know this. So I think there's 11-ish soft hazards from memory. I can't remember. So these are the soft hazards. So competency of the team. And I could have put this document and asked John to speak right at the start of the day in the competency this morning, but I felt these are risks to the project. And this isn't just structural engineers' risks, it's fire, it's M&E, it's client, it's project managers. People need to be aware, because I remember reading somewhere that 70% of all the failures are to do with competency of people, like mistakes people make predominantly. And this basically, I read this and there's just so much in it that I know he hasn't referenced certain documents, but I know where he's taken certain stuff from, because I've had those arguments as well. So it's kind of the competency of the team, resource, we're all familiar with that. Actions relating to the brief, making sure the brief is clear. Incomplete design, designed by others. For us in structures, I could act as a principal designer, and then there's certain elements that go out to a subcontractor designer. And if they're not working to the same codes, that's a risk within itself. One, it slows down the program. If we're having to check something that's been withdrawn for 20 years or more, and we're not familiar with the old codes. And if I'm not familiar with those, it adds risks back into the project. Assumptions, sometimes just ignoring those not on the drawings. Interfaces, again, we have specialist subcontractor design. So if you have, I don't know, pole design compared to our superstructure, what does that interface detail look like? Especially with working with existing buildings, making sure you get that new to existing building connection critical. That's really important. Change control documents, really important to keep track of changes, make sure they get recorded. It's little stuff, but from the guys that we spoke with, the guys who are on the call this morning, and I said, we record our CDM, and we showed you page 1, and then I said, right, page 2 is basically, it's all our soft hazards. We use them as a CDM risk, and there's stuff in there for design, there's stuff in there for construction, there's stuff in there for maintenance, and that way, when we do start having those arguments again with other members of the design team or the procurement process or whoever else, then we go, no, look, this is a hazard. We identified this as a hazard. This is why, to stop this argument. And so we're finding it really useful from that point of view as well. So that's why I wanted to get John on as well, because it feeds into the risk assessment, which is what I'm gonna just tip on now. And I appreciate we are probably behind a wee bit, so I'm going to try and scoot along as much as I can. Get rid of that. Right, you can go. Okay. Building Safety Act. So why we're doing risk assessments, where it's come from, and where we are at the minute. So when you go through the Building Safety Act and you read it all, it's not as bad as it seems. I think there's 229 pages, whatever it was. But these are the pertinent clauses regarding to risk assessments. So clause 83, there has to be an assessment made of building safety risks. And then there has to be a management of building safety risks. And we have to present the building safety risks that materialise regardless of the part of the building for which they are responsible. And we have to reduce the severity of any incident resulting from such a risk materialising. These get fed into a safety case report. And the safety case report should prepare a report containing the assessment of the building safety risks. And the meaning of a building safety risk means a risk to the safety of people in or about a building arising from the spread of fire and structure. Ta-da! This is where we're at. So it doesn't differentiate between new and existing, which really annoys me, and it doesn't differentiate between medium high-rise buildings. I might have touched on this earlier this morning, and I want to talk about this a little bit on discussion in terms of competency as well, because I couldn't do a 30-story new skyscraper. I know the principles of it. I could probably follow the process if someone explained it to me, but I know I wouldn't have the competency in order to do that. Equally, but I would be on the same register, and I could easily do a 7-story, 9-story, 12-story LPS system or existing building or something that doesn't comply with disproportionate. That I could be all over. And then, so it's really important because for me, they're massively different skills. If you're doing a new risk assessment, I think if you use these 3 existing documents from a structural point of view, you are 95% there. I think you'll get a lot from these. Now, the one on the left and the one in the middle are taken from 2013. And I'll be honest, the one on the left, I think I read in a couple of nights. I really enjoyed it. It wasn't techie. I mean, it is techie, but it was just an easy read. And it was really interesting. But they touch on a few of the stuff that Joe was talking on earlier in terms of type of occupancy, like all your typical risk assessment considerations, people, number, access, all this kind of stuff. Document in the middle is more theoretical, and it's grand, useful to flip between the two. You should really read these through in conjunction. And then the one on the right was published in November last year. It was the 2nd edition, and we were lucky enough to have the lead author on this call today, Ruth. So I know she was chipping away for some comments this morning in the chat. Hello, Ruth. And for those of you that know me, I also contributed a chapter to this book on existing buildings. So it's going to feel a bit weird for me to plug the existing building bit on this one, but stick with me. So for new buildings, I think there's loads of in there, and you'll get 90-95% there, providing you get the equations right and whatever else, you're grand. You're pretty much good to go. Existing buildings, however, when it comes to that, little bit more to it. I still think there's more work to be done. So document on the left, there's a chapter in there on existing buildings right at the end, and it's probably, I can't remember from memory, maybe 5-6 pages, a few pages, nothing mega. One in the middle, similar, few pages in it, talks a little bit about existing buildings and how to do it, and talks about a LARP and all this kind of stuff. And then the one on the right, big chapter on existing buildings, about 50 pages. It's states to use the risk assessment as the basis for assessing existing structures, but doesn't really go into it. And the one thing that I'd never got a handle on before I finished it, we were working on that, me and Ruth were working on that for about 2 years, and Kat, my colleague, she was checking it and basically my sounding board all the way through. So I feel it's unfair to me to a certain extent, is that I've already had all these questions are coming from 2 years experience of banging my head against a brick wall, working out how we're going to approach existing buildings and risk assessments. So, but I could never understand where to draw the line, and that was the big thing for me. So the one thing we did figure out though was a process and understanding where the risk lay when we assessed existing buildings. Now I'm going to focus more so on the existing buildings here. I'm going to jump into new, and then I'm going to flip back to existing to show you where the difference is. Now, the process with existing buildings was we couldn't figure out where the red flags were, so to speak. So, and we finally settled on where you have the existing building information. It's great, rarely happens, but if you do have it, we review that first. Then we do a visual condition survey of the site. And so looking at something on Google Maps is completely different to walking on site and seeing it. Even if I've got architects drawings and people proposing a chop and change or an airspace development or whatever else, and I've had it before with a client who's bought 2 buildings, looking to redevelop it, infill, do all this kind of stuff. And on paper, it looks great. You look at it on Google Maps, it looks great. They're perfect for redevelopment. You go on site and I'm taking bricks out the wall because there's more to it, just isn't there. There's cracks all the way through the building and all the stair course. It's just, I'm looking there at there's drainage all the way through all around the building and runs, and it's falling to bits. And I was just like, you can't do anything to this building. This building is just unsafe. It's borderline unsafe. And then, but once you're on site, it at least gives you an idea of going, okay, right, I can get in there for investigation and testing. I can take some brick samples there. I can dig a hole there. I can test that beam. I can open up there where we've access. And you start building the picture of the existing building and how it's working. And then that will then eventually feed into the feasibility report and or risk assessment, whichever you're doing. Feasibility report will be a change of use, how you go about change of use on a building and the feasibility in order to achieve that. And then the risk assessment is basically what we're doing for all the HRBs now and going, okay, where's the risk to this building? How are we going to mitigate it? And then we go from there. Risk assessment basically feeds into the feasibility, but we wrap it into one when we do any feasibility reports. But for the purpose of this, I'm going to focus on the risk assessment. And the one question I kept asking myself was, where do you draw the line on safety within existing buildings? Now, I know my industry in particular are pushing the green agenda. Every post on LinkedIn is sustainability, carbon content, how sustainable is your building, blah, blah, blah. And I'm not against it. I just want them to tell me where the line on existing buildings is for safety. Because until they can answer me that, how are we supposed to reuse existing building stuff? And it's just been a pet peeve of mine for a while, but I think we're there, and this is what we want to dig into today. So this is going to sound daft, but the risk assessment is almost the least important document out of these 4 considerations. So obviously, if you've got any existing building information, even especially in the older structures, it's incredible. Like seeing how they approach the building and what they use, different rebar, different material grades, that is priceless almost. Then you go into, for me, the condition of the building is most critical and the one that we need to keep an eye on. And when we say every building's different, this is where it's different. Investigation and testing will then feed into the findings from the visual condition survey, and then your risk assessment is basically, I still think you could take 2 buildings built at exactly the same time, same form of construction, same usage for 50 years. If one is maintained, they are still going to have the same risks, but the level of safety is going to be less in the one that isn't maintained compared to the one that is maintained. And this is understanding the risk, where the risk is in the building and how to manage it. And that's where I'm going to want to dig into. So in terms of the risk assessment, new build, I just want to go through the overall process of what we approach for a new build assessment. So in terms of the building regulations, we work from Schedule 1, point A3, which is disproportionate collapse, and we say that the building should be constructed so that in the event of an accident, the building will not suffer collapse to an event disproportionate to the cause. Right. In order to achieve that, we work from approved document A and then Eurocode BSE 1991 Part 1-7, which is Eurocode 1-7, which is accidental. I added this in during the lunch break based on our discussions from this morning. And when we talk about consequence classes, and Joe mentioned it earlier about how, I think you said it was like a 2-story care home versus a 25 residential tower are different. This is how we characterize the differences between a 2-story care home and a 25-story tower. So we talked about consequence class 1, CC1, a low consequence for loss of human life, consequence class 2, medium consequence for loss of human life, and 3, high consequence. And you can see some examples of different types of buildings. So I called them agricultural buildings earlier, sheds, anywhere where people do not normally enter, residential office buildings, and then grandstand public buildings, consequence of fire or high. And then this is taken from approved document A. I did this in that lunch as well, and it just, you can, houses not exceeding 4 stories, consequence class 1. Class 2, 5 stories, hotels not exceeding 4. Basically 4 stories, kind of the limit, apart from if you go in industrial, retail, or schools, and then you're kind of bumping it up to 2B. And then this is where the consequence classes increases, the requirement for more robust structures comes in. So this is where we're kind of taking it from. And I think if you guys, the fire guys, had something similar, it might be worth exploring, might be useful for you guys, I don't know. So this is approved document part A. Now, we talked about class 1, 2, 3. Class 2 is actually divided into 2 subgroups, so to speak, 2A and 2B. So when we talk about reducing the sensitivity of the building to disproportionate collapse in the event of an accident, there's no additional measures required for class 1 buildings, providing it's been designed and structured properly. Class 2A, I'm calling it your rough 4-story mark, but you'd have to go back and check it depending on the usage. It's again providing effective horizontal ties or effective anchorage of suspended floors to walls. I don't like effective anchorage other than prisons. It's weird that you used the prison analogy earlier. We use the same here because when we talk about effective anchorage, it's basically bearing of the floor onto the wall. And the difference between that and ties is that ties will, like, it could be rebar within a wall, or it could be steel frame with strong connections, but that's a continuous tie vertically or horizontally, and the wall laps into the floor, for instance. Or the floor is completely tied all the way through, like in precast concrete, and you basically put rebar through, you tie all the floor together. Effective anchorage was a mistake taken from the World Masonry Codes, and it was intended as good practice to put into class 1. And the government have come out and said this in their CPNI document in 2011. And so, but on the flip side, I use that as part of a risk assessment now in existing buildings, even modern buildings, and go, look, it's not a robust building because it uses effective anchorage, for instance. And I know it's in the proof document A, but this is one of those areas where, yes, I know what it says, but practically you could put ties in and it's incredibly more robust than effective anchoring. Class 2B structures, this is where we provide effective ties both horizontally and vertically. And then we also do the notional wall removal where we play Jenga with the building. More applicable to, say, timber frame when we put a ring beam round, or old masonry structures, for instance, and we try and justify masonry arching, or if the floor slab has capacity to span 2 ways away from the bit that's blown out. And again, we're looking for any kind of redundancy in the building that way by removing elements. And then it also kicks in permissible areas of collapse. So it's reasonable that it says, look, if there is an accident, yes, you're going to lose a wall or a portion of the building. We would permit 15% of the floor area of 1 story. And then if you're going over that limit, you got to design it as a key element. Key elements are basically designed for the blast loading. So we look at any adjoining walls, we take a portion of the load there. It might be a steel column. Typically it's normally a steel column because we tie it all in, and then we design that for the blast loading. And so we know that in the event of an accidental action, a gas event or similar, that is still going to remain and the structure doesn't collapse around it. A couple of walls might blow out around it, but principally the frame, the structure still stays. Now, we go back into Eurocodes, part 7, accidental actions, and there's an element in here about the risk assessment. So it also includes forces for the use of ties, permissible areas to collapse, which just reiterates 15% or 100 meters square, whichever is less. And then the criteria for the risk assessment just ranks from severe, high, medium, low, very low. Now, there are definitions of this in there in terms of what they consider severe to very low, in terms of repair to the building and floor areas collapsing. What I like to do is cross-reference it against this document, because this document gives better descriptions, so to speak. And it gives examples. So minimal or very low would be visible damage, cosmetic repair. Serious is where we normally draw the limit. So this will be, I don't know, a quantitative. This is all based off past collapses, and we understand how structures work. And so we know, right, based on past collapses, 15% of the floor area were allowed, or 100 meters squared, just there is the lesser. And this is where I spent weeks, months trying to shoehorn these limits, even the collapse of additional stories or a collapse of the complete story or anything else. I tried shoehorning this approach into existing buildings for weeks, months, and it just did my head in. I could not make it work because the existing buildings do not comply to this format. And so this book basically will kick you out, and as long as you're in the green and you stick to the right, I said the left side of the black line, so to speak, then you're grand. So you can see a serious event, explosions are considered rare events. So providing you're there, and basically if you're following, it's the prescriptive approach, so a compliance approach. If you put a steel frame in and you design the connections for this force, and you make sure you've taken this load on it, and you make sure that these ties are all the way around, good detailing, decent calcs. The calcs aren't even that difficult for disproportionate collapse, but it's just getting it detailed right and making sure the thing stands up, making sure you follow the build sequence and whatever else, and you're grand. Not much to it. This table, however, is basically the risk triangle, the tolerability of risk triangle. Now, one on the left, this is the ALARP triangle. This is for new building. A lot of people have seen this triangle. We have the risk levels down the right, ranging from 10 to the 8, -2, going up to 10 to the 2. Obviously, everything's acceptable, unacceptable, and a LARP in between. Now, risk is likelihood times consequence. And this is why I didn't like Joe's report when he sent it to me, because I was always told that whatever we produce isn't for us. So if I produce any calculations, any drawings, any reports, it's not for me, it's for the end user. And for me, if I'm reading that report, there's nothing measurable. And this is, I think, it's really important for clients now, because we're dealing with clients who, for us structures, typically higher risk buildings, the guys who do risk assessments for new buildings with 15 stories and above, they're seasoned developers. They're big schemes. If you're doing anything like that, you've got a good design team around you anyway. Everybody knows what they're doing. This is the first time in history where we've had to retrospectively go back and look at the existing building stock and make changes. And not just to the existing high risk buildings, they've also halved that limit down to 7 stories. So they're now bringing in a class of clients who have never really had to deal with this before, never had to think about risk assessment or understand how to look at risk and what that means and how to apply it to buildings. And so when I look at risk is the likelihood times the consequence. And so if I'm in a new building and there's a typical multi-story building and there's a basement car park, and if there's a vehicle impact and it causes a loss of floor area or multiple floors, then it might just kick in somewhere up here. The likelihood of that happening and the consequence of that happening might put you somewhere up here. In order to get rid of that, we're like, all right, let's just get rid of the basement. Let's get rid of the basement car park. All right, that's elimination. And this is the event control hierarchy. You've got to work top down. And typically work through the methods and do it that way. So you could go, right, I'm going to remove the basement. You'd be like, good, back to normal again. All good, no problem. Client's going to go, you can't do that. I want my basement back. Fine, tried. Substitution. Okay, can we swap the layout anywhere? Can we move the entrance to the basement car park somewhere else? Can we move it away from these columns? Can we get it away from the high risk stuff? Can we reorientate the access route around these columns, for instance? I don't know. Or can we incorporate that into a structure within the basement that protects these a bit much? That would be kind of like maybe a substitution route in terms of swapping stuff about. And it's really easy to do on the new build, because whilst it's still on paper, it's so easy to change. The difficulty comes when it's not and it's already built. There where the problems happen. Engineering control. So they are ties for structural engineers, ties for a building. For fire guys, it might be your sprinklers or monitoring systems or alarms or anything like that. And then you're into your admin. So admin would be putting a sign up saying, please don't crash into my column, maybe. Something similar to that, and then your PPE. And that's your hierarchy of control. And pretty much, I think if you follow the prescriptive and the routes recommended in the code, you make sure your connections can take all the forces, you design stuff as key element where it needs to. If you're doing notional wall removal, you've demonstrated that if you remove any wall rain there, the building still stands up. Then this is your starting point. You're at 10 to the 6. This is like year 1, off you go. And then this is all acceptable, and then you go and build it. And all your risk is at a nice acceptable level. If I had the same scenario in an existing building where I remove a column and I'm somewhere up here, I can't rejig about it. I can't put vehicle barriers in. I might be able to, but I can't. The risk is still there. It's still inherent. And then some of these might be off the table. Like I can't not put the car park in. I might be able to retrofit strengthening works, for instance, or something similar. But it gets a lot harder to reduce it from there down to here. You might not even get down to there. If you can bring it into the LARP or show you've reduced the risk as low as you can, that's the risk assessment in essence. Now, the HSC on their website, they talk about the difference between, they call it new versus existing plan. So principles and guidelines to assist the HSC in its judgment that duty holders have reduced risk as low as reasonably practical. So this is their own guidance. This is what they're working to, and I plan on throwing this back at them when they start arguing with me. But if we replace the word plan with building in this next text, it should be borne in mind that reducing the risks from an existing building as low as reasonably practical may still result in a level of residual risk which is higher than that which would be achieved by reducing the risks as low as reasonably practical in a similar new building. Basically, it's difficult to apply new philosophy to existing philosophy. Factors which could lead to this difference include the practicality of retrofitting a measure on existing building, the extra costs of retrofitting measures compared to designing them on the new building, the risks involved in installation of the retrofitted measure, which must be weighed against the benefits it provides after installation, and the projected lifetime of the existing plan. All this may mean, for example, that it's not reasonably practical to apply retrospectively to existing buildings what may be demanded by reducing risks as low as reasonably practical for new plan, and what may have become good practice for every new building. Right. I can tell you now, when I've seen reports from other engineers where they look at an existing building and they try and apply the new principles of, right, we need ties in this building, we're going to retrofit it with steel frame, basically put a steel frame within the skeleton, and then that's suddenly compliant. But then that steel frame is going to clash with ceiling heights, services. It's going to cause thermal breaks. It's going to cause acoustic breaks. It's going to cause fire issues because you're breaking all the compartmentalization. You've got to decant the residence. You've got to throw scaffolding up. You've got to figure out how to build it. All this takes, and basically the HSC this is your time, cost, and effort. And when you roll time, cost, and effort together, you get gross disproportion. So if the cost of all the time, cost, and effort to do this is greater than the point of gross disproportion, then they say, right, in regards to the risk, this is your level. So when you throw that together, I think you redraw the risk triangles based on existing buildings, and they look something like this. So this is where I've been trying to figure out where to draw the line on safety for existing buildings. Now, we talked about consequence classes earlier, and we talked about the importance of consequence class 3, and consequence class 4 is kind of like national infrastructure, national tragedies, and Grenfell would be 72 fatalities, and that hit the national news. And obviously, that's what triggered the Building Safety Act, and that's why we're here. So we don't want that happening again. So I think if you draw the line on the risk triangle and say, right, my hard line is consequence class 3. When I look at an existing building, I'm not accepting of any scenario, when I consider a scenario, structural fire, that goes into the unacceptable region. And if it does, that's my trigger. Right, you got to go repair that. You got to go fix that. And I think that's a fair assessment, and I think you can build from that. And then at the same time, if you're if you look at the event control hierarchy, then you're looking at where is the point of gross disproportion for each scenario. Now, the iStruct only want to give the technical solutions to this, so to speak. So they only want you to demonstrate, yes, this is how you do your risk assessment, and you recommend your ties or your mitigation efforts or your engineering solutions, whatever your outcomes are going to be. That's where they want to draw the line. I'm saying you need to go further, because if you don't have an appreciation of the point of gross disproportion, it is going to drastically affect your choices of remedial work to the building. If you don't understand where that is, and if you don't understand where the line is drawn, then you don't know what risks you need to reduce as low as possible, and you don't know what risks you need to address. And that's really important for us. That, for me, is the start of it. You got to draw the line somewhere, and this is where we're drawing the line. But at least that I can translate that to clients and go, look, this is why we're doing what we do. And remember, risk is likelihood times consequence. So when I look at any gas events, I know the likelihood of a gas event is 1 in 1.51 million, which translates to 0.00007 or whatever. I'm somewhere down here. So it's really hard to justify a whole building structural collapse if you're removing one wall or one column. And I'm fully aware you may get a full building consideration within fire, for instance, but it's really difficult to get within structure. So it's how you look at it and how you're looking at the building in regards to that. And this is how we're looking at it. And I'm yet to have this argument with the BSR, but if there's logic behind it and there's sensibility and we're not cutting corners and there is still safety at our heart and where we're going, this is the route I'm trying to push and where we're going for. So when you read HSE's 1170 report, they talk about risk assessment and what they want to see in terms of the existing buildings. And there are specific structural and fire considerations in there. So in terms of the structural, it's checking residential floor or common floor areas between the two. If a local floor collapse, what happens then? Multiple floor or whole building floor collapses, balconies and suspended walkways, attachments and supporting components to the facade. Specific incidents, which we consider, say, vehicle impact. They don't mention disproportionate collapse due to fire, but that is one consideration that you need to throw in as well. And then this is where me and Joe had a few discussions on this. It's like Joe will give his risk assessment report that says high, medium, low, whatever. I can give my risk assessment report and say, right, this is the risk, this is the value of risk. And the reason I think we need to be more aligned is if I'm a client, who do I listen to? Is it fire? Is it structural? What do I address first? Where's the risk? How do I know what's high risk compared to low risk? So I think if you make your risks numerical and you actually give the value of risk, at least it gives the client then something measurable and go, okay, right, I've got a bigger risk from fire here than I do structure. I'm going to address this first. That's higher up in my LARP triangle. Then I'm going to bring it down. And that will feed into their maintenance or operational strategy. The client should be doing the cost benefit analysis, which drives the point of gross disproportion. But the amount of work we put in for the risk assessment in order to work out the actual risk value, I think it's like 2 extra factors you put on. It's not a hard calc, but it at least allows you to steer the conversation, have that chat with the clients, go, okay, what can we do? What can't we do? And obviously your geometry of the site, your physical restrictions would dictate what you can and can't do quite a lot as well. And obviously the layout of the building. And then I think all this is leading into risk and asset management on the client's behalf. So we can talk about point of gross disproportion. We could talk about putting money in, and at the minute I'm seeing the industry just throw the kitchen sink at existing buildings. They're seeing what sticks. They're going, no, we want everything. We want ties, we want sprinklers, we want second stair core, they're treating it the new buildings. They don't work. It's not going to work. I agree you can draw the line at consequence class 3. We don't want consequence class 4 buildings events happening. Great, no problem. But then over what term are we supposed to be managing the risk? 1 year, 5 years, 10, 50? Codes and regulations could change again in another 10, 15 years. What happens then? Are we clients, building owners and everybody else expected to change with the regs again? Like, where are we drawing the line? What's a reasonable assumption in order to manage these risks over? That's a big discussion point for me as well that we've kind of got to. So, and that's the least important bit. So that brings us on to visual conditions survey and investigation and testing. So when I talk about the visual conditions survey, we touched on this earlier about the assessment for existing structures, and there's an international code out there. And I talked about the plausibility check earlier, when something doesn't work and you go, it should do, what's it doing? There's more ruder versions, I call it, but it's basically a nonsense check. Within this report as well, you have target reliability. And we actually use reliability in new build. It's clause 2.2 in Eurocode 0, basis of structural design, and it's a principal rule. So we allow for reliability in new build, and reliability is a measure of how safe a structure is. So in new build, you start around about here, 10 to the minus 6, you're at 4.75. And then that's, you can easily relate this back to the arc triangle. That's the bottom of the arc triangle. 10 to the minus 4, that's the top of the arc triangle. So this gives you something measurable to tie in risk and safety in terms of the building. And this is where we're kind of going through, and this is how we're measuring it. And this brings us all kind of back to the circle. When you, and this is what I was talking about, you can plot reliability on this arc triangle. And then when you investigate and test, you could easily test any fabric, any material fabric to get the actual reliability value, and you know how safe it is. Now, for us, there's a difference between risk assessments. I can look at the risk of a car hitting a column at the ground floor, and I can tell you the risk value is here. And if you put up barrier bollards in place, it reduces the risk. I'll be honest, we're not a risk-based industry per se. This is going to be a big shift for all of the engineers out there, especially. But so I know it's the quantitative measure. I know I need to study quantitative risk assessment in order to understand how much it reduces the risk by, but it's a bit above me right now. But I can say, right, we can do a risk assessment and we can reduce the main risks to the building. I think that's one exercise you do straight at the start, work with the clients, look what systems got in, look at the building fabric, look where the risks are. And I don't think they're going to change too much from a structural point of view once you've had a really good one done. And then it becomes a case of, okay, well, what does their maintenance plan look like? What does their asset plan look like? How is the client going to manage the building for the next 10, 20, 20, 50 years? And obviously in that 10, 15, 20, 50 years, your buildings degrade, materials degrade, timber rots, steel rusts, masonry cracks and weakens. Where does the building lie when it's 100 years old, 150 years old? Like, what's the risk level then? What are we saying is an acceptable level of safety? How does that feed in with how we approach maintenance to the building? So we think, like, we've discussed this, and I remember having a really good chat with Ruth on when we were writing the book, and we were talking about the importance of visual condition surveys. And there's a bit in the building regulations that say you're not allowed to make existing buildings worse. And she made the point of saying we should reword that, saying you can't leave existing buildings unsafe, because that implies you could have an unsafe building. By not making it worse, you could have an unsafe building and not do anything to it. So, and that just stuck in my head. That in my head, then I had a base level of safety. Where are we talking a base level of safety on existing buildings? And I mentioned the example of 2 buildings earlier, one that's been well maintained for 100 years, one that hasn't been well maintained for 100 years, same construction, same use, everything else apart from the maintenance. This one's fallen into disrepair, this one's in good condition. Where are you drawing the line? Okay, and how you manage that. So for us, we're going down the reliability route, and that's why. And okay, I want to go back to this because the iStruct came back in January, and I've been emailing the technical director, Patrick, at the iStruct for a few months now. He must be sick of me. But I know they were going the reduction in partial safety factor route. And we spoke about this morning. It was one of the questions, and I said I'd come back to it. Now, for me, we talked about partial safety factors and how we add them to design elements. And we spoke about the fact that there will be some elements. Let's take a timber joist floor, for instance. It might be 100 years old, it's sagged, it's bent, it's bowed, but it's still stood up. You check it against the old code and be like, it says it shouldn't be working because the timber sections are so small. You check it against the new code, you'd be like, it doesn't work to the new code. That's the plausibility check. So you go, okay, right. Now, in January, the iStruct came out and said, right, we will permit you to reduce the partial safety factor. How much safety is in that element? So you could get the new code to work now if you reduce, say, the factor of safety from, I don't know, 1.4 down to 1.3. Now, that might work. You might look at that and go, great, that works, cheers. Most engineers will go, cheers, thanks very much. It doesn't tell you how much longer that timber joist is going to last for. It doesn't tell you when you should be next looking at it. It doesn't tell you if you're going to get another 2 years, 3 years, 5 years out of it. And this is why we're trying to push reliability. And we're still learning this, but this is our application. This is why we want to do that rather than the reduction partial safety factor route. Because for us, it gives us a better idea of the building, and it feeds into the maintenance requirements, which are part of the risk assessment as well. And we can draw our own base level of safety dependent on each building. So when we say each building is different, the condition of each building is different. The risks are pretty inherent, pretty consistent across most, and you'll get the odd difference between some properties and that, but the condition is what's going to change. And if it's been chopped and changed over the years, that's a big risk as well. That's why they need to be checked. So then it's how we feed all that information back into the reports below. So back into the visual condition survey, back into investigation testing, back into the risk assessment. And then what are the outputs? Like, what are the steps going forward for the clients? So do we need to strengthen? What are the remedial works from both the visual condition survey and the risk assessment? How do we monitor? How do we plan for the works? How are we implementing a maintenance strategy, which is constantly under review? That's client's responsibility, remember, but it's got to be fed in by us. And then firming up the risk and asset plan, and then the how to present that to BSR. So if you've got risks within the LARP zone, you'd be like, yeah, I know that's a risk, but look, this is my plan to mitigate that risk for the next 5 years. And I think these are the discussions that we should be having with clients, and then firming that up before we go to the BSR. And that's where we're at the minute. Thank you very much.
Cheers, Sean. Thank you. I'll scribble in some questions down there. If there's any in the chat as well, to throw them in. We've got one from the chat from Mike. If you've got some questions in you, Sean, still going?
Yeah. No, absolutely.
Fantastic. Okay, cool. First question from Mike. So at what point would you oh, hang on, it just moved. Where's it gone? At what point would you need to do an intrusive assessment of primary structure, having completed the visual condition? And then he follows up and says, are there any red flags? For example, LPS systems, etc. But any red flags you'd have?
Yeah, so some buildings are more susceptible to, okay, 2 parts to that question. So the first one was intrusive works, was that one?
Yeah.
Okay, so intrusive work. So I would do, when you look at a building, I can look at a building and I know roughly how it's framed. I know from the age of construction, we'll do a desk study, we'll see when it popped up on the maps, and we're like, okay, this is a 1930 building. It popped up in 1935, likely it's going to be built to these codes, these regs. We're going to check wall thicknesses. We're going to check, we've got a rough idea of how that thing was built and what it was built to. And then the visual condition survey will be picking out points going, okay, why are you not working? Why are you cracking? Why are you moving? Has there been any remedial work in the past? We've got, and I would say bar concrete buildings, most of the buildings should work fairly linear. Like, floors are going to span from here to here. And so you should have a good idea of if the walls all line through the building and the structure of the building. I think I would then do a quick load takedown. Like we spoke about earlier, if there's any areas that are in distress, or a really thin wall at ground floor, you'd be like, that shouldn't be working. Why is it working? They're the triggers for me. They're not red flags. They're just triggers for me to do investigation and testing. Red flags, I would count for change of use. So if you're adding on stories to a building, if you're making chopping and changes to the building, there's loads of red flags in that, such as transfer structures, that I look at and go, right, no, we can't get access there. I know that's a red flag. Don't touch it. Go away from the building. And I'm happy to have those conversations with clients, and I've told them to walk away of more than 1, 2, and a few. And then the bit about LPS systems, the LPS precast panels, we spoke about it earlier. And we spoke about how they were susceptible to wind as well as blast. Basically, they're not connected very well. They all just stack up like a cards. And they are at risk of, they're more susceptible for fire and a disproportionate collapse, for instance, because once everything warms up, it kicks it out. And that eccentricity means it's just going to possibly kick out and collapse. So yeah, that is a risk. And so that's when we have to speak to you guys and go, all right, have you considered a fire here? What about this? What about that? And I still think that that's more of a risk. I would say wind's more of a risk in the higher risk buildings, multiple stories. than it is, say, 7 to 12, 15 maybe. I'd say once you're probably over 12, 15, it might be becoming more of a risk. But again, it's understanding, okay, how's this building working? You're almost putting the calcs to it. The calcs, I told you earlier about the old boy who rang me last night, and I thought he was going to chew me a new one for my opinions on LinkedIn, and he was a big fan in the end. But he was saying that you can have opinion once you've done the calcs, and that's it. I think calcs will tell you everything you're going to do on the building, and I think it stands in good stead. I think if you're not sure, run it, understand it, and that the more questions you ask, the more calcs you run, that will point you to where you need to go in and do intrusive works.
Perfect. You know, I've just remembered a question I had earlier. We've got more questions, but one that I want to pick up on wind you mentioned there. You were talking earlier about wind and the prevailing conditions it comes from and all that kind of stuff, and it's fairly standard. When you do that, do you consider the environment that it's in? Like, have you ever stood at the bottom of the shard on a windy day and it's more blustery than on a non-windy day and you have build-up of all of that? Does that come in, or does that breach beyond structural engineering? Do you consider it?
Yeah, so the specialist wind guys in there, there's so they did it on the shard. They stuck in models in a wind tunnel, and they also looked at the future redevelopment of London and analysed how the funneling effect will affect buildings, and especially buildings around it. So yeah, that was a big consideration as well. So I think they had to be considerate to surrounding buildings and not to overload or concentrate wind load on additional buildings. It's beyond our work, but yeah, it is out there.
Yeah, I meant to ask earlier because there was a famous case in Leeds that I'm aware of where they constructed a high-rise building, 25, 30 stories, I think it is. No, not quite that tall. But then there was a fatality at street level because a car tipped over, and it was because of it. So there's now these fins over the road, and it's that interface between, I don't really know whose role it is, specialist wind input into what we do as well in our disciplines. So yeah, I meant to ask that earlier. Sorry, I've called back to. Some more questions though. So Thomas Bradford's just asked, what resource do you use for old maps to find out when the building popped up? I think we were just talking about there, wasn't it?
Go to EnviroCheck. So all EnviroCheck have bought all the free old map software websites out there. So we used to use oldmaps.com or whatever it was, and then they got bought out probably a couple of years ago. But you could, if you stick in the postcode, it's like 140 quid. You'll get all the old OS grid maps from that have ever been produced on that postcode, and then you just go from there. Gives you the best way we've found to try and identify a building, unless you have the original building records.
That's really cool, actually, isn't it? To be fair, like, what a resource for you guys to be able to pick that up. Really good. Okay, I want to pick up on a point you made that I think you said it was Ruth that made it about non-worsening clause in building regs and about whether we're satisfied with that. I know it's a discussion point as well. Just say the point again. So it was about not just non-worsening, but getting to a minimum level of safety, because we have this same battle in fire about, well, you know, there's not sprinklers there now, so let's not put them in, but let's just put extra fire extinguishers. If we're 1% better, we've won. How do you approach it in structures? Do you do that base level assessment, or how do you interpret the non-worsening clause of building regs?
Yeah, so the clause is you're not allowed to make existing buildings any worse than they are. And I think it's building work, clause 4-ish, I think it's in there. And so basically it falls under, that's it. It's building work, but it falls under the change of use. So if you're doing a change of use, for us, they point you towards Schedule 1, and they say, right, if the building was compliant with building regs, Schedule 1, thanks, Ruth, clauses 4, 5, 6, then you say you've got to still make it compliant to building regs. I think that's the part B. Part A is in there and saying, right, if the building didn't comply with this part of building regs, then you can make it no worse than it was existing. So that gets you into the whole, when we extend buildings, for instance, in airspace, that's when we look at the consequence and go, right, if we're sticking additional stories above a building that didn't comply, we can check vertical loading, we can check lateral loading, the existing building might work, but then we still have the risk from disproportionate collapse. If there was an explosion in the existing top floor or the new build story above that, what happens then? How are we managing that risk? And so when we talk about not making an existing building worse, like, some people will just go like, look, I've justified all the risk, we're not making it worse, but you don't know the condition of the building. And that's the difference. So yeah, we spoke about it briefly with you guys. For the equivalent of you guys, it's going around making sure there's fire breaks in there, or doors are in good nick and they haven't been kicked about too much and stuff like that. That's a base level of safety. So it's almost going around and going, right, what are we working with? Have we got 2 layers of plasterboard and stuff? What have we got? Where's that level of safety? What are we working with? And then you're building from there. But you're making sure all that is working as it should be. And for us, that's a visual condition survey. So we'll put in stuff like, okay, this needs to be maintained, that needs to be refurbed, that needs to be repaired, that needs to be strengthened because it's been had a rain pipe leaking on it for the last 20 years. stuff like that, that gets you back up to where the building should be.
Yeah, I mean, we've had the same on I don't know if I've talked about the project, but it's very similar. So extension project going on, upward extension. I said I need to go into the external wall and assess what's there, and it was thrown at me and said, we're not touching that part, so let's just leave it and it's no worsening. But what I said is I have to satisfy myself it's to a suitable standard, because if it's still, if it doesn't meet the standards at the moment and we're not worsening it, admittedly, yes, that's the case, but I still have to satisfy myself it's got a base level. Same with sprinklers. There's no sprinklers existing, we're not going to put them in, it's no worse. Well, yes, but what if at the moment they really need them? What if it's currently a really low level of safety? I'm not going to accept the non-worsening clause. So yeah, I know we've discussed this before, but yeah, okay, perfect. And then the last one I want to, we'll pick up on and say about the condition surveys. So as we mentioned in fire, we go and do a regular risk assessment. We usually go annually, but it's constantly happening. Is there anything equivalent for structures? Do you do a kind of standard by rote, you check it every X number of years? Or is it just if you are to do building works, you'd go and do some intrusives? Is there any periodical inspections that you'd do for structures?
No, so I mean, typically we are introducing as part of our maintenance now on HRBs. This is a question we've been asking ourselves. So especially with reliability, we're trying to draw the line as to, okay, where's the risk level lie in reliability as the building gets older? And then we need to tie that in with degradation and rates and understanding how stuff degrades and condition of the building and tying all that together. And this is why I have a maths tutor at the minute, because some of this is just like, I just need a little push just to get over certain bits. But for me, it's just kind of like, I think it needs to come in. I think it needs to be part of the maintenance program, because I don't think you could. The one thing I've read from all of this in terms of risk mitigation is no big event happens on its own. It's always a series of smaller events. So for instance, if I had let's take CCTV surveys, for instance. If you get those done every 5 years, it will show you any cracks occurring in your drainage. If you get that repaired sooner, it's going to be a lot cheaper than underpinning your building in the next 2, 3, 5 years, which are what, around £1.5 a pop, or whatever they are. It's silly stuff like that. So yeah, it's kind of like where you're drawing the line and getting better at that. And I think that's where we're having to check with clients in terms of their maintenance.
Yeah, absolutely. A big part, material degradation is really interesting. It's a big part of my research group, because we test materials the day they leave the factory. So you test a piece of cladding and it's the day it leaves the factory and that's the specification it meets. Put it on a building and weather it for 2 years. You remove that outer surface, you expose what's underneath. Same with the door, same with the wall, same with the structure. Once it lives and breathes for a while, it changes properties entirely, doesn't it? So that kind of ongoing preventative maintenance it is important. Ruth just made a point as well in the chat. I'm gonna read it. So a building that may have once been code compliant when built may have become unsafe due to multiple alterations or degradation of materials. I think a structural engineer has a duty to point out issues like this when they spot stuff in a building. So that's from Ruth there, talking about exactly the same thing you're saying. Yeah.
Yeah. So, and stuff like, especially masonry buildings, they're so easy to chop and change. And buildings there's no infinite chopping and changing you can keep doing to them. They become less robust. We got to be sympathetic sometimes with what we're doing to the buildings and then maintaining a base level of safety. So yeah, it's kind of what we're doing.
Yeah,
I'm half looking at Trevor's and Ruth's chat on the side as well, but I haven't.
Oh, can you see it as well? Oh, I was reading it as though you'd not seen it. Sure, I thought that would be a big reveal. But yeah, if you can see these guys, I quite like what Trevor's just said. Actually, it's about doing the right thing, not just doing the thing right. I like that, actually. To be fair, yeah. Perfect.
Trevor, I'll come back to your first point. I know it was lengthy, but I'll come back and read it as well after this.
Excellent. Well, that's all the questions actually, Sean, on that last session. So that wraps that one up. So back to you.
Nice. Right, we were due for a break, and we were due for a break at 3, but we ran over. So why don't we've got? Do you want to take 15 minutes and kick off at say 25 past, and then we'll run through till 5. There's a few discussion points I've noted down from today, and then and then we'll just go from that. And then if there is anybody else in the call who wants to come in or has points, throw them on the chat. We'll try to bring you in as well where we can. And go through that.
I think the last part of it is just a discussion. Is it an open forum? So if anyone does have points they want to raise and wants to chime in and unmute and all that kind of stuff, that's the opportunity, isn't it? So anybody that wants to come in as well is more than welcome. That's the aim of the last session.
Cool.
Brill. Okay, cool. Speak to you shortly, Sean. Hopefully see some of you guys back as well. See you shortly.
Discussion points that I thought Only three really I kind of want to go back over. So risk assessment output, where they draw the line on risk safety for existing buildings, and then competence training and demonstrate competence when not chartered. So I know we rejigged this all about last night, but whilst we're both fresh off risk assessments, can we kind of dip into this? Because I thought the bits for me going forward are how are clients supposed to differentiate between fire and structural risk? Which do they prioritize? How do they prioritize it? Risk levels need to be stated for each scenario, which was one idea. I think that's easily done. Recommend the meeting between fire and structure before both risk assessments are issued. And then maybe I would throw the client in there as well. Just go, look, this is where the risks, and it might explain the hierarchy, and then that should feed into safety and the client's maintenance and operational strategy going forward then in terms of what they're going to address, and then also what term risks are taking over.
Yeah, it's been a really good point actually that you've made today about put yourself in the client's shoes. If you get two different reports using two different methodologies, how do you prioritize? And of course, if you ask the fire guy will say do the fire stuff, and if you ask the structures guy, he's going to say do the structure stuff. So what's the metric? What's the common methodology you can adopt that allows you to? Because if my scale's 1 to 5 and your scale's 1 to 10, there's no alignment there. And I think actually we've highlighted a couple of things. This isn't scripted, I promise. We didn't choose this, did we? But by accident throughout the day, we've had bits and pieces where we've said, well, I do that as well, like with the structural oversizing of timber. So I think if we're talking HRBs, it is a meeting in front of the client to say the output is going to be this from fire, the output is going to be this from structure. How does that align? Can you then make a decision off the back of it? Because if I have a high risk, but it is to a totally different scale to your high risk, I mean, I said earlier how scary structural fire engineering is for me, because in my mind, it's the whole building goes. A high risk for fire could, in theory, like we talked about with fire risk assessment, the surveyor might determine that a fire extinguisher in the wrong colour is high risk. Well, that's not proportionate to the risk of a building collapsing. So yeah, some form of unification would be great. I don't know the answer, but yeah.
But in your different colour fire extinguisher, what would the consequence of that be then? So if you had a different colour fire extinguisher and it didn't work, or it was the wrong fire or whatever else, be like, okay, is the potential loss of life there one person? Is that the risk there? Or is it more? I mean, I know you're playing different assumptions and different scenarios, but then wouldn't that give you, you're like, okay, it's 10 to the minus 5, it's 10 to the minus 4.5321 or whatever it is. Would that not give you the differentiation?
Yeah, you could do. And I pick fire extinguishers intentionally because it's one that I often see in a fire risk assessment, but they're not actually required under building regs. They're not something that's there. It's something that's as a mitigation. So you'd never have that as a high risk, or if you did, I'd suggest it's wrong. But you could quantify it. I mean, there's no reason you couldn't have a common scale between fires and structures where if you had 10 to the whatever, you assigned it that way. It's still subjective, of course, unless there was really detailed guidance on it. But I don't see a reason you couldn't align on it. And the thing that you've mentioned a couple of times about put yourself in the client's shoes about having to make a decision. Do we add sprinklers or do we strengthen the reinforcement to the upper story? But, you know, whatever it is that you need to do, how do you make a decision? So, yeah, it would be a useful thing to do. I'm not going to claim I know how to do it. I'm not going to claim I'll email it to you tonight. But, yeah, agree that would be great, wouldn't it, to get aligned?
Well, for us, it's quite easy. The likelihood is already calculated from, we take it from R2P2. HSC's R2P2 document. So, and that's only really that. I'm guessing for you guys, it's looking at the likelihood of fire. That's why I asked earlier about, do you go back and look at the likelihood of fire with that decreasing trend that we saw this morning?
Well, okay, so pick up on the design fire stuff I was talking about. You could work out the likelihood of fire, but then what's the likelihood that happens after that? Because if you run the same test 10 times, you get 10 different fires from the same ignition source. So you'd have to do what's the likelihood of fire, and you could get that from fire statistics, fire data. You can make some assumptions, but then you'd have to run it a number of times. We quite often do Monte Carlo analysis, where you sort of run the same design scenario 1,000 times and pick what's the most likely outcome that you'd have if you're doing some modeling of it, for example. So it's perhaps harder for fire because you've got the initial likelihood that a fire occurs, and then you've got 10 different ways in which the fire might grow. 9 times out of 10, it might not spread beyond the compartment fire origin. So do you always design for the worst? Because then you can always come up with a towering inferno scenario. You can always assume somebody's left the door open and it hasn't been maintained, and the smoke control's broken, and it's the day the sprinkler's drawn down. So there has to be a limit to it, but you could define the likelihood of fire. It's what happens after that. It's how you determine what then is the base case of severity afterwards.
You just touched on something like the fire doors could be open, there could be an ignition source, it could be this, that. What's the limit on assumptions? Is there a limit on assumptions? Like the window's open, someone drops a flaming box of matches, there's a crumpled up newspaper in the corner. All these assumptions and all these stuff, like, is there a limit? Because I know you said you could quickly get to full blazed inferno, but
yeah,
like, is that after the 10th iteration or the 6th iteration, or what? Or how do you apply that? Or where do you stop? Because then because you could quickly make the case for sprinkler staples, whatever else, very quickly.
Yeah. You could never stop, couldn't you? Because when we do modelling, we were talking earlier about CFD modelling and how we determine smoke travelling through a building and things. You assume a door opens and 20 seconds later it closes. But what about if somebody drops something in that door and it never closes? Or what about if the fire service run their hose through it and you've got a 500 mil gap? Or you could come up with an unlimited number of scenarios of what would happen in the fire because it's so variable. And then what happens if the fire just burns itself out? What happens if the window's open, or what happens if the window breaks? So sometimes windows break, sometimes they don't. If the window doesn't break before the sprinklers activate, it's unlikely to ever break. You get an underventilated fire. If the window breaks early in the fire because it's 2 meters closer to the window and the window is single pane instead of double glazed, then you get a totally different fire. So the number of variables you would never stop, I suppose. But the likelihood of a fire occurring, you could quantify. It's what happens after that that's tricky. You could do so many iterations on it.
Yeah. No, I was just thinking of that. It's like you had like 260 to 70 whatever deaths last year from the population due to fire. Okay, is that a likelihood that you're going to be killed in the fire? Could you work from that and go, right, give the client a high level overview and go, this is our risk, this scenario, X amount of people are going to be killed, this is the likelihood, this is what I recommend. At least in my head, that at least we can rank your stuff and my stuff. And go, and then push fire here because structure, we're good for this right now. And then that feeds into the maintenance plan and go, right, next 5 years going to implement sprinklers, we're going to upgrade, there could be repair work from the structural side, for instance. Also, I'm on a risk course next week as it happens, so I'm probably asking questions that will come on next week as well. But cost per scenario. So when we talked about the point of gross disproportion earlier, and it's something I'm going to bring up next week anyway, but so I appreciate there aren't unlimited deep pockets like in public sectors where they just throw the money, they make it work, and it needs doing, it's doing, when they're dealing with the public sector. So, and I had this chat with Patrick, the technical director at the SPHStructures, briefly, in terms of he thinks the point of gross disproportion is typically taken from industry, from the public realm. So it could be different. It might even be less for the private sector, and it's already low. It's not a big number when you start running through the numbers, and so it's but I don't know if you apply that number per scenario, or I know if you could put a mitigation measure in there and it might sort out 3 scenarios in one. So I want to try and understand that a bit more as well.
Yeah, I suppose what you're saying is, like, if you put sprinklers in and you do the outlay of cost, it might solve 3 or 4 different scenarios. It prevents the fire breaking out in the first place, it suppresses it if it does grow, and also it assists with firefighting. Whereas if you don't put sprinklers in, you try to mitigate each of those, you're then paying for a dry riser for the fire service, enhanced compartmentation for the spread of, and limitation on materials or something. So you can solve 3 problems with one thing. So you can do that. I mean, we get increasingly drawn into cost benefit analyses these days, particularly in existing buildings. Is it more beneficial to do X or Y? And we get drawn into that. There isn't really an established methodology on that, but yeah, it's exactly the scenario we just said there. So how many problems does it solve? How many non-compliances do you hit? Something like sprinklers are great because when you look at the 5 functional requirements, sprinklers are a bit of a novel one that assist with all 5 functional requirements. They make your means of escape safer because it increases the ASET, makes the building safer. It wets the materials, so they're less likely to combust. It reduces the fire size, so you need less compartmentation. It reduces the compartment temperature, so you have less external fire spread. And it's a firefighter in every room is what they call them, isn't it? So you start it. So you get some solutions that are more heavily weighted for safety. as opposed to compartmentation, which impacts some of those, but doesn't really benefit all 5. So you could assign a greater risk rating in terms of benefit to different solutions that you adopt in. And that's what we're increasingly asked to do in fire. Again, I don't know anyone else on the call is the same, but I find in fire, I'm increasingly being asked to do that for existing buildings, HRBs especially. Do we strip the cladding or do we put sprinklers in? Do we do waking watch? Do we do additional heat detectors? Do we do this or that? And it's a cost thing, because as you say, there's not unlimited money for these things, and they are costly. Millions of pounds being spent on some of these, you know.
Yeah, risk appetite of clients. So from a designer point of view, we could sit here and we could recommend whatever measures to implement this, do that. Let's say the client doesn't want to do it, or tenants don't want sprinklers, or they don't want to dry, so they're happy where they are, they don't want all this kind of stuff, they don't want to be disrupted. I would say, I'm purely from a selfish point of view, I know I'm covered, I recommended it, but then is there a risk appetite from the clients in terms of they carry that, and are they at risk if anything does go wrong from the BSR or HSE or anything from that as well?
I think if there was a missed opportunity to upgrade an existing building that wasn't taken, I can see that coming back in future. Similar to you probably, because I'm head of my firm, you're head of yours. We spend a lot of time writing careful wording, don't we, in reports and fee proposals, and solicitors write them for us, that kind of thing about this is what we told you to do. You're paying me for my advice, you don't have to do it. You know, I'm not forcing this upon you. I have no, somebody asked earlier about authority and power. I don't have that. But yeah, I take it back as well, though. This is a bit sensationalized, but what if I turned the news on and that building was on fire, and I'd advised and I had the opportunity to recommend, and I backed down? So I'd always stand my ground on that. And similarly for a client, in terms of risk appetite, these are, I mean, you mentioned Grenfell earlier, international news, still is in the national news, still is international news as well, in fact. The thought of turning it on and that being one of your buildings on the news, and living with that, not being able to have the opportunity to do something and not taking it, is what I think feeds the risk appetite. I see risk appetite these days so much lower than it was practicing 10 years ago, because of course it is. You know, you expect that, don't you? People are far more risk averse now with safety critical things in buildings. And they have a higher legal duty now. There's now duties on clients, there's duties on residents, there's duties on consultants under the Building Safety Act. So far more risk averse, I find. And so, but then so are consultants, so are insurers, so is everybody, because you don't want your name on that sort of thing, do you? And we're all fed by the insurance industry, the market, the wider contemporary consultants, other disciplines, clients. Yeah, unlike working pre-Grenfell, it was slightly different, I found. A bit more, you know, risk appetite out there, far less these days.
Yeah. Also, Ruth, if you want to get involved in this discussion, you're welcome to hop in. I'll just change the permissions if you want to hop in. Because Ruth is also building control, so she sees all these submissions come through.
Yeah.
Well, she is happy to say a bit. Right, 2 secs. Hang on, I'll add you in. Nothing to do with me being tired. I'm losing my voice. Right, you should be in. You should be on. You're on
And
mute.
you can hear me now?
We can hear you. Hello, Ruth.
Hi, Ruth.
Yes, okay, hi. Mike, I don't think my camera's on, is it?
Yeah, it's on.
It
Yeah,
is.
Oh, is it?
it's on
Okay.
there.
I think I was just, so I work in building control and I'm a structural engineer. And I think the things that I'd like to reinforce are what we'll come on to existing building safety cases in a minute, but it's that soft risk thing, and also an element of laziness amongst structural engineers. So the Institution of Civil Engineers has a document that tells structural engineers what should be part of a Part A submission. And I see a lot of engineers taking real shortcuts. And I think they should be embarrassed professionally, to be honest. You know, we're professional people. We can earn a lot if we do our job properly. And there's an element of structural engineers feeling downtrodden, charging low fees, and they're not doing a proper job, which I just don't think is in the spirit of being a professional. And as Sean said, and as John Carpenter said, it's almost all out there. We have the ICE documents of the Institution of Civil Engineers document on Part A submissions. we have John Carpenter's soft risk document for which I think was for Cross. And so if we move on from the laziness of engineers, it's also then those interfaces with secondary structures. And I think only last week there was a Cross report about balconies not being fixed properly to buildings. So there needs to be one design engineer who has overall responsibility for the whole of the building design. And if things are contractor designed, that design engineer needs to still be involved. So I think that the Building Safety Act is actually an opportunity for engineers to really take ownership of what they're doing and to do the right thing. Now, coming on to safety cases, most engineers can use design codes. They're even easier to use now because, of course, we have software. And so I think that the new skills that engineers need to focus on are actually understanding the structural performance of a building. How do you actually think the building is working and how will it work? And framed structures are relatively simple. And to be honest, even if you don't have design drawings for a framed building, you could probably make quite a good assessment of how safe that building is without the set of calculations or even the design drawings. With a masonry building, they can range from, let's use the prison example again. Hopefully none of us will see the inside of a prison other than for engineering reasons. But think of an old-fashioned cellular type building where all the prisoners were in little cells. A masonry building like that is hugely robust. You know, it does horizontal ties and any steel work that a modern building would need, because you've just got all these little units of masonry. You know, if you knock one wall out, you're definitely not going to have 15%. I mean, we know it's difficult to knock a wall out of a prison. That was the whole point. You're not meant to be able to escape. But masonry buildings got more and more flimsy, and then of course people have altered them. And I think some of the riskiest buildings are flats, well, houses that have been converted into flats in London and other cities, where everyone has sort of had a bit of a fiddle. And so I could imagine that there'd be the situation where a safety case report for a modern steel framed building could potentially be a couple of pages of A4. I mean, that's hard to believe because nothing, but you know what I mean. Whereas a safety case report for a 5-storey residential building carved out of a Victorian property, it could run to pages, and it could run to visual inspections, testing, and creating your own drawings. So I think it's about I think structural engineers and fire engineers approaching these safety case reports need to not have a one-size-fits-all approach. I think it will vary hugely on the size of the building. And I think you've just got to understand how you think that building is working. And if there's not something you don't understand, you need to find out what's going on. Listening to Joe and Sean talking, it makes me think these reports need to be a joint effort. Like you say, Joe, if you go in with one sort of scale of risks, and Sean, you go in with another. I mean, I do feel for these clients because they often owners of larger developments do have some expertise. You guys will actually be getting into quite a technical level that I don't think even someone who's been involved in construction for 30 years would necessarily understand. So it just struck me that these reports probably need to be coordinated, and that you know, the HSE has always said it's a fire and structural risk assessment, and perhaps now is the time that structural engineers and fire engineers really come together. And then finally, I mean, I obviously know quite a lot of structural stuff, but Joe, I found your fire session really interesting, so thank you for that. I felt it explained lots of things in about 5 minutes. Well, not 5 minutes, but it's like, oh, you made it very simple. So thank you. Anyway, that's all I got to say.
I didn't know which way that sentence was going, Ruth. It was, I found your fire presentation very, and then I thought, oh, the hairs on the back of my neck are going here. But no, thank you. I appreciate that. That's the intention today. And Sean, I know, has done the same for fire engineers, because I've had some people reach out to me. So that was the hope. So yeah, I'm glad that that's.
Well, I think we always have a tendency to get really complicated too early. And I mean, it's like Sean's morning presentation. There's actually only A1, A2 and A3 of the building regulations. And again, your illustrations there were really good. You know, this is what slope stability is. I mean, that picture spoke 1,000 words, you know. So yeah, anyway, thank you. You can turn me off now.
No worries. Cheers, Ruth. Let me just kick it back out. Hang on. The next level of topic I was going to talk about was base level of safety, but I think we've talked about that a fair bit. We exhausted that in the questions and we've gone through it, and I think we roughly know where we're at. For us, it's good practice, and I read through Trevor's comments in the chat as well. And what did he say? It was like, it's about doing things, doing it. You say, Trevor,
doing the right thing, not just doing things right. I think it was that way around.
It's about doing the right thing, not just doing things right. Yeah. So the right thing, I still think you need to bring existing buildings up to a level of safety, up to where they should be. First and foremost, they give you a base to go from, and then you can make your assessments, risk assessments and stuff from there. Because that was one thing when me and Ruth were working on the book, and I needed somewhere, I just needed somewhere to jump from. I needed somewhere for work. I need to know this building's all right. This is safe. It's sound structurally. It's sound from a fire point of view. If it's not, this is what you need to bring it up to that level. Okay, and then we go from here. That's the intention. So that's how we're kind of working it. And I think, and then that's why we push. If some clients will push back and they don't like the visual condition survey, like they don't want to pay for it, and they're like, nah, this is the most important document for us. This tells me where your leaks are, where your cracks are, if it's moving, and it's just, and this should be the document that's repeated. You talked about frequency earlier, and like, I've read a few stuff saying 5 years and this, that, the other, and 15 years, but we're still, I think it also depends on form of construction. Some buildings more susceptible than others. But yeah, that's.
Can I ask a question about your testing? Ruth just mentioned it then as well. If you do testing of existing structures, what does that testing consist of? Presumably you do sample testing from across a beam or column, so you take away a sample of it, I guess, and do some testing elsewhere. Do you then do visual survey of all parts? Because you could have a single point of failure, couldn't you? You could have the tie-ins of one particular column or beam is the failure mode of that structure. So do you have to do quite an intense, when we do intrusive fire risk assessments, we do 10% of doors, or we do X amount of fire stopping or whatever. How does it work if you were to go to an existing building and potentially do some testing of samples external?
So bearing in mind, we can't take more samples are the better, but obviously we still need to leave a bit of the building behind and not remove too much.
Well, that's what I was thinking, because like for a fire thing, I can take it away and I can kind of patch it up and make it as good as, or accept I'm taking it from a non-critical area. You guys can't take a column away to test it because you need the column. So like, how does it work practically? This is me just asking, picking the brains of a structural engineer.
So masonry will try to take something roughly 3 courses by 3 courses type thing, and then that's normally what they want, and they send that to a lab, press tests, and they might even do chemical analysis on the mortar and tell you if it's lime, concrete, and a lot. So that will give you your strength, and then 6 to 10 samples of any material. You could do your standard deviation, then work out your mean strengths and everything else, and then that feeds into reliability. So that would be masonry. Concrete, you can core drill through. Steel, you wouldn't necessarily take obviously the whole column, but you can take, I think steel is like 120 mil by about 50 mil, something like that. So you could do lots of those samples, and if you know where to pick them in the beam, again, it comes down to how hard the beam's working. So if you know, like here, for instance, if it's near the support, it's not working hard at all. So I'll do that, but that will feed into maintenance. And when we spoke earlier about the LARP triangle and how material degrades, it's like, okay, when do we want to do material testing to make sure this thing's still all right? Or is it at the point that it's degrading? Is it the point where it's falling apart? Where are we drawing that line? And then we go, okay. And then we go, actually, we thought we were at this level. We're slightly better. But then we might get another 5, 10, 15 years. And that feeds back into your survey stuff then.
And you mentioned earlier that if you go to a site and you see a brick is just hanging out because the mortar's gone, is it those kind of indicators that would make you need to go and do a survey? So you cracks forming and subsidence and that kind of stuff. Is that what might lead you to do more intrusive investigations?
Normally, so that one was an airspace job. So I went just due diligence, so to speak. But you would normally expect the building manager, owner, or whoever's looking after the thing to call us anyway. It was riddled with cracks. Like I felt uneasy walking through the stair core kind of thing there. It just, yeah, it wasn't. Yeah, I should stop walking into dangerous buildings. I don't like them.
I've been on your Instagram though, Sean. That's all you ever share. There's pictures of you in dangerous buildings all the time.
That's quite, oh, no, it's just it's my adrenaline rush. That's all it is.
Life of a structural engineer, eh? Yeah, okay, that's useful. Thanks for asking. I know that wasn't on the discussion points, but again, I meant to ask earlier about that sampling and how you do it. So yeah, it's useful to know.
And then the final point I've got on here at the minute is competence. So, you know, I'm going to throw this one up because for the benefit of anybody who wasn't here this morning, share this, do that. Okay, so for the benefit of anybody who wasn't here this morning, the secondary legislation brought in by the Building Safety Act has now brought in Chapter 3 of building regulations, secondary legislation, and they've brought in 2 additional requirements. They've brought in behaviour, and then clauses 3 and 4. So behaviour we touched on earlier, we think you can get through that with code of conduct, pretty much. And we said we're going to look at what other institutes do and how they're approaching behaviour as well, because it affects us all. And then, but clauses 3 and 4 talks about people in training. Now, I thought this opened up a whole can of worms in terms of if you're in training, I assume you're in training to become chartered with your institute. What does adequate supervision look like? Is it 1-to-1? Is it 1-to-6? How are you managing teams where you have non-competent engineers working on the job? If you have old boy engineers who are very good and run rings around you, but they're not chartered, where do they fall on this? How is this going to be enforced? So is everybody supposed to jump on? So I know the IC and the SPHStructures are both doing a register that we're supposed to jump on, prove our competence, and then we're eligible to work on high risk buildings. If we don't, is that a client risk? Who's going to enforce this? How are old boys going to do this? Who's checking training work? How do clients ensure the right people are on the right job? That's it. Yeah. So yeah, that was, I think this could either be a massive issue or it'll get swept under the rug.
Yeah, the competency one's the biggest. I've just been asked to attend a conference and speak about competency. It's the biggest kind of thing that's going around at the minute.
Drop my slides.
Say again.
Drop my slides.
Oh, that'd be good actually, Sean. If you could send them to me, I'll cross out SPH and just write Delta on it. I have a bit of a take on this about competency because I'm somewhat cynical in everything in life, and I, professionally as well. You can do 10 years work in 5 years, or you can do 10 years work in 20 years. Like, you don't know the measure of somebody and how good they are is not how many years they've been a consultant or an engineer or whatever it is. And I think have I told you this before? So I used to work for an airline. I used to be fire safety in-house fire engineer, and I used to talk to pilots a lot. Did I talk to you about this, Sean, the other day?
No.
I've always found this interesting that if you speak to a pilot and you say, how long have you been a pilot? They don't give you it in years. They give you it in hours. Have you ever heard of that? I've got 10,000 flight hours. I've done 10,000 flights in a Boeing 737. And when I worked for the airline, we changed from Boeing aircraft to Airbus A380. And all those same pilots went back to saying, I've got 200 flight hours, because they have to relearn the aircraft. And I do the same for engineers and their work. Because if you've done 10 years, but you've never worked on a HRB, you are as green, potentially, as a graduate who's got a year's experience and never done a HRB. So how many flight hours have you done on that type of project? And I've always had this, and I've always thought about it, but I'm seeing it more and more with work we're bidding on. So professionally, for a second, we're doing PQQs and things like that. What are your last 5 schools that you've worked on as an organisation? And the engineer that's going to lead it, what are their last 3 REBA stage 4 fire strategies they've written on? And having to demonstrate specific competency, not just the wider letters after the name, how many years experience, etc., etc. I think it used to be 5 years was a badge of honour, 10 years was, oh, you're climbing, 20 years is listen to that person more than anybody else. And I'm seeing it more and more now about demonstrating competency that is specific, especially for HRBs. So we're being asked, how many buildings over 7 stories have you worked on? We've just bid on a 35-story building. I just submitted it over the weekend. With that bid, we had to say, have you worked on a building this height or taller, to demonstrate equivalency? So I always push flight hours. I always say, if I interview someone, for example, how many years have you done? I've done a year. What kind of year have you had? How many projects have you done in that year? What was your role? How many, things? I encourage that to demonstrate competency, because I've done, I don't know, however many fire strategies, hundreds, thousands, however many it is. But I wrote my first football stadium strategy last year. I'd never done one. and now I've done 2 in that last year, and I didn't have any competency in it till last year. You can forget stuff as you get older. Yeah, that's happening a lot to me as well, to be honest. But yeah, so competency wise, I define competency as specific competency. You can be a really competent fire engineer but have never designed a school, so you are not competent in writing a school fire strategy, because there's so much variance in the work that we do, right? So that's my take on it, at least. That's my
I think it's going to be ultimately it needs to be client led, and mostly clients will know they have their own engineers they work with, their own architects, their own design teams they kind of work with anyway. And I think if they started exploring out, and if this was a new requirement, they'd probably explore out to see who they, and ultimately it comes down to relationships and who you're going to work with. But I think not necessarily a tip box exercise. I think it is good. I think it should be brought in. But like, I really like John's soft hazards, because it basically puts it just highlights all of the arguments you typically have. And I think if you can use those right and put it in the CDM regs and communicate that, and it's almost knowing where the battles are coming down. It's like, if I put down, I do a loading plan, I've got connection forces for a steel frame. I know if the contractor isn't, let's say, if the contractor hasn't read the national steel specs, I know he's going to come back and go, where's my connection design? This, and they're like, it's in this document, it's in that, you should know this is your responsibility. And on one hand, it shouldn't be up to us to know all this, but on the other hand, it also makes your life a hell of a lot easier if it kind of does. And so that's kind of like all the soft hazards in terms of doing all the awareness and that. And then the one bit I thought about quite hardly with when I was writing the chapter with Ruth, and I was going to give the chapter a light touch, and that chapter, like the first edition of that book, is I think 60, 70 pages, something like that. My chapter was 50 pages in the end of the new book, and I was going to give it light touch because I didn't want to give anything away. And the thing that made me kind of like change my mind, and I just threw everything into it at the end, was I don't like seeing there's some buildings out there that shouldn't have been extended. So from an airspace perspective, and it scares the hell out of me. And that's why I was like, no, right, this is the process. This is how you're going to do it. And I spoke about internally with Kat about this quite a lot. Like, how much do we give away? How do we not? And they're like, you know what? We do nothing. It's done right. And that's where we're going to go. And you can lead a horse to water, but you can't make it drink it, so to speak. And so, and I think if most of the time I think it's like we solve headaches for clients. It's like, it's not our opinion. This says that. This says that. Why aren't you doing that? And to be honest, if someone is argumentative, they back down pretty quick. So, but yeah, I think we spoke about it the other day in terms of reports and the race to the bottom and where you stand on this. And I was like, I just think I know reading those reports what you're going to get. I also know on certain jobs that clients can have to employ a second engineer because it's like see you later, gone, and you don't hear from them again. So yeah, I think this is stuff people should know anyway. So I think if you can demonstrate that, and I think it's a fair question. I ask it from, if I have steel fabricators approach us and they want us to recommend them on future jobs, I ask for their competency, and if they give it me, and I know that it tells me what they've read and what they haven't read, not just steel certificates and stuff like that. So I think if you encourage it within your practice, it will probably partner on throughout the industry, and that's the only way we're going to raise the level. But yeah, it's a group effort, so to speak, on this, I think.
Yeah, well, I think it was you that said to me recently, Sean, about Judith Hackett talking about don't wait for regulation to come in, just change as an industry. Like, the culture should change, don't wait for regulation on it, which is exactly what I know lots of us are doing. But yeah, exactly the way it should go. Peter has pulled me up on my flight hours very correctly as well by saying you can work for a long time and do very bad work. In truth, you can normally tell a very bad pilot because they don't reach 10,000 flight hours, because yeah, for pilots it's easier. But agreed, again, behavioural qualities in addition to when I push for it, for example, and actually this PQQ I did last week for this job. Give us an example of 3 buildings you worked on that are similar and exactly what you did. So exactly what was the stages you worked on as an engineer, not just, oh, I did a QA check of it and I'm going to put it on the CV because it looks nice. You know, where were you? How many meetings were you in? Did you come in at Reba stage 2, see it right the way through? Is the building, you know, operating as it should do? Were there any issues? So yeah, I'll clarify, thanks to Peter's comment about the idea of having this specific kind of competency related to what you're bidding on and, you know, the work that you're doing, but also the quality of that being there as well, because everyone can, well, not everyone can do bad work. I suppose you can, but anyone can blag that, you know, competency and just, you know, not actually clarify what they did on the scheme.
Yeah, we have that. I've just thrown the feedback form into the chat. If you can grab 30 seconds and fill that out before we finish it today, it'll be much appreciated. There is 5 questions on it. 2 of them are berating, and I think it's if you want to hear from us again and what you thought was interesting and everything else in between. And then, but yeah, what you were saying then just reminded me of our chartership. Show me exactly what you've done, and that is the only time we're taught to use the word I've done this, I've done that, I've done this. And I don't know if it's the same with you guys, when you can just look at drawings and just know if they're wrong or if they're missing something or what they've done. But I don't know. I was having this chat with non-engineers ages ago, like at tail end of last year, and they were saying, I think I was talking about language we were talking about language in work, and they were asking if we swear and stuff like that, and I said it really depends. In that, if you go, I can go on site in the morning with all the labourers, the contractors, and all the red top papers lying around, and if I don't swear at them, I'm not going to get my point across. Then I could walk into a design meeting in the afternoon, learn through all the technical stuff, not a problem, talk your language, talk architect's language, go from there. And then in the evening, it might be client drinks, and client drinks are really personal. It depends who you're with or not. I said, but anybody can be a contractor. Anybody can be, like, me and you could set up tomorrow and sort out a contracting firm, but it doesn't mean we're competent in contracting. And this is what I think this is the biggest issue in the no worries, Doug. Thanks, mate. Don't know who Doug is, but he's going, so I feel like he's stuck with us. We should say goodbye.
Good work, Doug. Good work.
And I think that's the biggest issue. Anybody coming into the industry doesn't necessarily have to have read everything we do. That's why clients pay us to read all this. So if we're demonstrating we're competence, yes, here's my fee because I'm competent. I have read this. This is how we incorporate that. This is that. And it's almost like, fine if you want to go elsewhere, but this is our level. And that's how we're kind of using it at the minute. And I don't think that's too much to ask in a certain sense. It's just finding the time to put it together. And then, like, there's 2 of us at our firm, me and Kat. And I think I've said this to you before, that work just feels like it's fueling our reading habit right now. And we read our arse off at the minute. But I don't think we would be here still if we didn't, because the new work sector's dried up, refurbs flaky at the minute, top end of the market's gone, bottom of the market prices coming up. So that bit in the middle where everybody's trying to fight in through, and we're just getting there off our competency alone. So there's merits to it for that reason. And I think even if you don't get jobs, if you're educating the clients, at least they're thinking about it. So from that respect, I don't think it's a bad thing.
Yeah, I mean, they're the clients to stay in with, I find. So our team's slightly bigger across Delta, but we have the same battles of who do we work with, who do we align with, what work do we chase. For me, it's the clients that want the quality. I mean, again, we've discussed this. We're now discussing it in front of 40 odd people, but as soon as people try to argue you down and race to the bottom, I'm more than happy to walk away. And we talked about a client that we've both done it to recently, who we won't name, of course, who have said, can I have it cheaper? And you go, yeah, you can, but it's not me. Like, you go and find it somewhere else. You will be back in future when it goes wrong and you need a peer review or a second pair of eyes, but it's entirely up to you. So it's aligning with those clients and collaborators that you want to work with. I know
you mentioned it earlier about turning on the TV and seeing one of your buildings on there and it scares the life out of you. Same reason. And we don't do simple stuff. We do all the high risk stuff. We take on that, and it's just some, like, the number of heart in the mouth moments I've had over the last 5 years, maybe, with projects we've worked on, stuff me and Kat are doing, and pushing new techniques, trying to figure out a way to justify existing buildings and the like. It's just there going, is this right? Is this sensible? Is this safe? Are we doing it right? And it's that, and that's difficult to get across sometimes.
Yeah. The reading habit, though, is fantastic. I mean, I've seen your CPD log, so I know exactly how much CPD that you do in you guys over there at SPH. It's amazing. But yeah, you need that. But you also need the reassurance of people around you as well. So, like, other contemporaries in industry, working with collaborators, all that kind of stuff. It shouldn't be siloed, should it? It's we're thinking of doing this. Does it work for you? I'm fortunate in a sense because I work at the university and I teach so many other people in industry who are from other consultants, and we get to talk about it and we talk quite openly, and it's great that I have that. That gives me reassurance. If other people are doing the same and they're not calling it out, then I feel vindicated by that. But yeah, it's important that chain is maintained, isn't it, with other people out there?
Yeah, we use I mean, that's why we use Ruth as a sounding board quite a lot. It was like, what about this? What about that? And it's a two-way street. She'll ring me every now and again for an hour, just like, what about this? What about that? But it's that I knew when I did the the existing chapter book and we were talking about airspace, for instance, and trying to work out how to approach all that. I was like, this can't be my voice. It can't be me against the industry, because I know I'm going to get bullied by all the big boys eventually, and they're going to go, no, yeah, you do this, and the weight reputation will just weigh in. So in a sense, it almost had to be all or nothing into the book and the approach and going from there. And we're slowly getting to the point now where it's just they're like, no, this is the process. This is good. We're going to stick to this, and off you go. But that's come from the readings, come from the competency. So we're in stupid, selfish way. I'm comfortable with our competency where we're at the minute. I think it's just going to catch a lot of other engineers out, because I think when we go back after this and we look through all the attendees and see who's there, I would put good money that most of them are fire guys. Its structures are just, I don't know if they don't care. They don't think building safety act affects them. I was talking to a few guys from the IC here on the call today. They're here because of that, because even they're slow to it. I think structures are quite slow to it as well. I know structures are doing a day-long fire conference next week. So Kat's going on that as well, and we'll learn a bit more about that. And yeah, we'll go from that. I know you care, Peter. I can see it.
Is my gang bigger than your gang, Sean? Have I got more fire engineers, more fire on here than structures?
Yeah, I think so, definitely.
What about structural fire engineering as its own discipline, though? Because it is. I know people who just do that purely, and it is a blend of the disciplines. And perhaps that person, I've got someone in mind. It would be unfair to name them, but I've spoke to them recently. They said, I probably don't know enough to be a structural engineer or enough to be a fire engineer, but I understand how they work together. And I said that in itself is like a superpower. Like, you probably couldn't go design a school fire strategy. You probably couldn't go and do a full assessment of, existing building structure, all your load calculation you talked about today. But structural fire engineering in itself is an emerging discipline, I suppose, but is a superpower. Under the Building Safety Act, like we talked, like Ruth was saying about getting us in the same room, it becomes its own discipline, doesn't it?
Yeah, there's so I think so Kat's trying to comment as well, and the two boys she's going to listen to next week. I think I saw them talk a few years back, and I think they're based at a university, and I saw them in their own lab doing a talk on structural fire engineering, and it was, I think they were talking about temperature differences and steel connections and all this kind of stuff.
Yeah.
And it's one of those, you can sit there, you can follow it, and I'm just there going, geez, you've gone down a rabbit hole here, like that you're not going to get back out of quite easy. And I definitely think me and you are going to have to work a lot closely together, to the point where if we're doing risk assessments, then my first question is almost going, okay, who have you got for fire? And then it's almost going, okay, when are we meeting? What are we talking about? When are you doing a report? Should we even go down the site together? Because me and Kat have discussed about putting stuff we see in our reports, not necessarily like major fire considerations, but we're like, look, this is us considering fire, and we can at least feed that back into, and then you can tell us it's not a problem, it is a problem, thanks, might miss, whatever. But that's us considering fire as well. Is about to has a very long engineering, which is also part of the master's degree. I saw that, Ruth. Yeah, I nearly signed up for it, but I need to get some work done as well. But I'd be interested to know if anybody does go on that CPD.
It's a very good course. It's a very good CPD course. Yeah.
Yeah, because Sheffield, I don't know why, they seem to be smashing it last few years in terms of existing building approach and fire engineering at the minute. I saw a guy talk on intrusive works from there. Irish guy, he was great. He just knew his stuff inside out. Listened to him all day. But there's only so much you can say about ferro scanning and all this kind of stuff. But yeah, he was really good.
Yeah, excellent. Yeah.
Structures module. Ruth, do you sure you don't want to come back in? I saw they've got a structures module in existing buildings as well. For their undergrads. We're still learning about it post-grad. Yeah. Yeah. Anything else you want to pick up on?
I don't actually know. I fielded a lot of it in the questions, and we sort of the discussion points we prepared in advance, didn't we? And we thought if they come up during the day, then that's those ticked off. But we've covered a lot of them along the way. The discussion points are there, aren't they? I suppose if anyone else has any other questions to throw them in, or any other thoughts, if anyone wants to dial in and throw things out, do feel free as well.
But what about if we throw Dana on or Rosie from the client perspective? Do you guys want to come on? You can throw something in the chat.
Well, that sounds really cruel, Sean. So well done for leading the charge on that for the guys. So
look, Dana's already thrown Rosie under the bus.
Good work. Do you know what? One of my biggest takeaways actually on that, if they do choose to dial in, is the client side that you mentioned, Sean. Like, what happens when a client get these 2 reports and can't coordinate them? Should we coordinate them in advance because we have that duty to our clients?
Cool. Yeah, I think we covered more of the discussion in the questions than I think we realised, but it was a good start. Also, reminder, guys, if you can do the feedback form, just so that if you do want to listen to our ugly mugs again at some point going forward, we will consider it. I think there's something there in the consequence classes in how we both appraise buildings and classify buildings in terms of their risk, from low, medium, high. I think if you guys aren't using it, I think that'd be useful if we can incorporate that. I think outputs, figuring out, maybe it's one meeting at the start, one meeting at the end of the risk assessments. What was one thing we were talking about earlier in terms of there might be, that was it, the part 2. For us, it's all the part 2 fire stuff in our codes, and just sitting down and going, okay, how does this apply to you? Can you fit into this? Do you not?
Yeah, I'd be quite interested in doing I'll call you on it separately, but doing a case study together on that and just seeing basically if we get the same answer is what I'd quite like to do. Yeah. Maybe I've got my lecturer head on too much, but I want to set us both an exam and see if we get the same answer, compare notes on it.
Dude, I don't need homework coming away from this. It was bad enough prepping all this as well on the whole.
Everyone gets homework. Did you not tell them? Everyone on this call gets homework. They've got to submit it. There's a deadline and everything. I'll give you a grade.
I know, I didn't tell them that on the link that we put up.
Gutted.
But yeah, I think we can definitely feed into that and then we go from there. Yeah, but I think I'm all done. I think that's it. I'm all talked out.
I think that wraps it. Well, we've discussed before doing this sort of thing semi-regular, or at least doing a series of them. So the feedback forms are useful because if it was useful to anyone, we have plans to do future ones, don't we, as well? Sean, and also potentially other disciplines and all that kind of stuff. It's all in the spirit of just free CPD for the benefit of everyone. I've learned loads today, to be fair, about the structures. And hopefully everyone else has done the same. So do fill in the feedback form. Good feedback, bad feedback, it's all useful. And potentially we'll do this again. This is what Sean and we do this a lot anyway. We just thought we'd invite people in to listen this time. So yeah, that's all that this has been, hasn't it? Just a note sharing sesh, but with on Teams with people dialing in. So it's been fun.
Don't tell them it's a bit weird that we prepare slides for each other as well. It's just a bit too much.
We meet at a restaurant in Manchester and prepare slides as we did last week. In actual fact, we did last week. You brought your laptop and showed me a load of slides about reliability. Trying to have breakfast.
Well, it was important. It feeds into this.
It does indeed. But yeah, so do let us know. Please do fill in the feedback. If you've got any comments, let us know. And potentially we'll be back on doing this again sometime soon, I reckon.
Yeah, I think so. No problem.
Good man. Appreciate your time. It's been fun. Cheers, mate. And thank you everyone as well for being here. Appreciate it.
I'm going to leave the chat up for what we are now, 4:15. I'm going to leave it up till 4:30, give everybody a chance just to hit the feedback form and everything else. And I'll sit here reading the comments and everybody going as well. And we'll go from there. Thanks very much. Appreciate you guys coming as well and supporting us. It means a lot.
Good job. Cheers, guys. Thanks, mate. Speak to you soon.
Cheers, guys.
See you guys.